How did Earth's oceans become the cradle of life? Where else in the cosmos might hidden seas endure? What other worlds hear the pull of tides as we do under our moon? From space, our home planet drifts into view as a serene blue marble. Vast oceans wrap around its surface, gleaming under the gentle sunlight. This water blanket defines Earth's appearance against the dark void. In the silence of the cosmos, our world's most striking feature is not its lands or clouds, but the endless expanse of shimmering blue. It is a tranquil sight, a planet dominated by ocean, cradling life in its deep waters. Long ago, before any living thing walked on shore, Earth's oceans were already here, stirring under ancient skies. We imagine the primordial rains falling on a cooling earth, collecting into warm, newborn seas. Those first waters may have steamed and churned, covering the young planet in an oceanic embrace. Over time, the tumult settled. The skies cleared to reveal an endless horizon of water, gently rippling. Under the soft light of the early sun, these primeval waves lapped against barren rock coasts, patiently shaping them. Life's story on our planet begins in those early seas. In sunlit shallows and deep, dark trenches, the first simple organisms found a home in the water. For millions of years, the ocean was the only world that life knew. Even now, billions of years later, the ocean remains a cradle of biodiversity, nurturing countless forms of life from the tiniest plankton to the largest whales. The sea is a living soup of possibilities, where life first learned to thrive. From the vantage of space, Earth's seas reveal how special our planet is. They give Earth its vibrant blue glow and regulate the rhythms of the whole world. Oceans carry warmth from the equator toward the poles, calming the extremes of climate. They breathe moisture into the air that falls back as rain, nourishing forests and fields on land. In these ways, Earth's waters create balance, a harmonious system that has allowed life to flourish over eons. As we gaze upon Earth's vast oceans, it is natural to wonder about seas beyond our world. Our planet's waters have proven to be the wellspring of life and stability here. Could similar waters on other worlds play the same role? Earth offers a template, an archetype of an ocean world brimming with life. In the quest to find life elsewhere in the universe, we carry this image of the blue planet with us. We look to the stars and ask, where are the other blue worlds, the alien oceans under distant suns? But before venturing outward, our journey begins with understanding the oceans close to home, for they are the key to imagining what seas on other worlds might be like. We live on a planet where the ocean's presence is constant and profound. Even when we are on dry land, the influence of the sea is all around us. Every second breath we take is filled with oxygen produced by tiny ocean plants far out at sea. The rain that waters our crops and quenches our thirst is first lifted from the ocean by the sun's warmth. In these ways, the distant waves touch our daily lives, quietly sustaining us from afar. For countless generations, people have been drawn to the water's edge. We stand on the shore, feeling the sand between our toes, and watch the endless procession of waves. The ocean inspires awe and humility, a vast, moving mirror reflecting the sky. Its horizon beckons us to explore beyond the known. Our ancestors set sail into the unknown, guided by stars and driven by curiosity, discovering new lands across the sea. The ocean nurtured not just our bodies with food, but our imaginations with the promise of what lies beyond that far blue line. The sea has shaped our myths and stories since ancient times. We imagined great monsters slumbering in the abyss and deities ruling the waters. Every culture has tales of the sea's power, of tempests and calm harbours, of creatures real and fantastic. These stories reveal how deeply the ocean has influenced our collective dreams. In its depths, we projected both our fears and our hopes, using the mystery of the water to understand our own nature. Oceans also mould the physical world we live in. The climate of Earth is regulated by the ocean's currents, which carry warmth and moisture around the globe. A warm current in the sea can mean gentle winters on a faraway coast, while a shift in ocean patterns can bring rains or droughts. In this way, the water that circles the planet ties all regions together in a single, ever-moving system. Our weather, our seasons, and our environments are woven into the fabric of the world's oceans. Life itself is a gift of the ocean. In Earth's youth, it was the sea that provided the chemistry and stability for life to begin, and long after, it was the ocean that cradled the evolution of diverse creatures. Even the first explorers onto land, ancient fish venturing onto muddy shores, came out of the water. Our own bodies still carry the mark of that ocean origin. The salt in our blood echoes the saltiness of primordial seas, and the water within us reminds us of the ocean we came from. We are, in a sense, a way for the ocean to experience itself walking on land. Understanding how deeply water has shaped Earth and its living beings fuels our desire to find water elsewhere. If oceans have guided the destiny of life here, perhaps somewhere on another world, an ocean is quietly nurturing life of its own. Our home waters stir our imagination and drive us to seek other seas across the cosmos, wondering if they too have stories to tell and lives to support. In this way, the ocean's influence extends beyond Earth, guiding our search for company in the universe. When we first set out to find other oceans in the universe, it made sense to start close by. We looked to our neighbouring worlds, the Moon, Mars, and Venus, searching for any sign of water. Early sky observers even imagined seas on those distant orbs. Through a telescope in the 19th century, some thought they saw dark patches on the Moon and straight lines on Mars, mistaking them for lunar mares and Martian canals filled with water. These were illusions born of hope, but they show how eager we were to find another blue world next door. As we gained the ability to send spacecraft to those worlds, we discovered a harsher reality. The Moon turned out to be dry and barren on its surface, a silent desert where no oceans ever danced under the sky. Venus was cloaked in thick clouds, and probes revealed a scorching surface hot enough to melt lead. Any ancient oceans there had long since boiled away into its dense atmosphere. Mars, the red planet, held the most tantalizing hints. Though today its surface is a cold, dry wasteland of dust and rock, robotic explorers found evidence that long ago, Mars was different. They photographed giant dried riverbeds and canyon networks carved by flowing water. They found minerals that form only in liquid water and rounded pebbles that once tumbled in streams. There are polar ice caps of frozen water and thin frosts that appear on winter mornings. All these clues whisper of a Martian past when rain fell from clouds and rivers coursed through valleys, perhaps gathering into lakes or even a great northern ocean. The realization that Mars was once wet and possibly Earth-like for a time fired our imagination. If life ever started there, it might have had a chance when water was plentiful. Mars became a focal point of our search for ancient alien life precisely because of its water history. We learned an important lesson. A world can have oceans in its youth and lose them later. Planetary climates can change drastically. Friendly seas can vanish, leaving only ghostly traces etched into the landscape. This made us wonder about other planetary fates, including our own Earth's distant future, and sharpened our resolve to find water in any form it might persist. Even on worlds without open seas, water finds a way to linger. In recent years, we confirmed that the Moon, though airless and dry on the surface, harbours pockets of ice in the eternal shadows of its polar craters. Tiny amounts of frozen water, likely delivered by long-ago comets, hide in those dark recesses. Mercury, scorched by the sun, also has ice tucked away in its poles' nighted craters, where the sunlight never reaches. Water, it seems, can cling on even in unlikely places, waiting for us to discover it. Why this obsession with water? Because wherever we find liquid water, we think we might find life. Follow the water became the guiding mantra for scientists seeking life beyond Earth. Water is the great solvent, the medium in which biology as we know it dances. And so our exploration plans have often been guided by where we might encounter this precious liquid. We examine pictures of distant moons for the sheen of ice or the flow of past floods. We sniff the thin atmospheres of planets and moons for hints of water vapor. We send our robotic emissaries with drills and spectrometers, all in an effort to answer a simple question. Is there water here? And could it still be liquid somewhere beneath our feet? As we searched our solar neighborhood, we began to realize that the obvious places, open oceans under a warm sun, might be rare. Mars taught us that a world could have had seas eons ago, only to lose them. The Moon and Mercury taught us that water can hide as ice in darkness. These findings nudged us to broaden our vision. Perhaps, we thought, if liquid water exists elsewhere, it might not always be on the surface like Earth's oceans. It could be concealed, protected beneath rock or ice, away from prying eyes. With this new perspective, scientists turned their gaze toward the outer solar system, where giant planets and icy moons awaited. There, far from the sun's warmth, another force, the pull of gravity, was quietly at work, potentially keeping water in its liquid state in the most unexpected of worlds. Night falls on the seashore, and a full moon rises, silver and luminous. Its gentle light dances on the surface of the ocean. Standing by the water's edge, one can sense a slow change. The tide is coming in. Wave by wave, the sea stretches a little farther up the sand, as if drawn by an invisible hand. Hours later, it will retreat again. This rhythmic breathing of the ocean, the daily rising and falling of the tides, is a subtle reminder of the cosmic forces at play, even on our peaceful shore. The moon, hanging in the sky, is the orchestrator of this movement. Its gravity reaches across 250,000 miles to tug on Earth's oceans. Though we cannot feel that pull directly, the ocean responds, lifting into a bulge that we experience as the high tide. On the opposite side of the planet, another bulge forms, and in between, the waters recede, creating low tides. This constant push and pull is like a great slow heartbeat, driven by the moon, and to a lesser extent, the distant sun. It is a force that has quietly influenced life for eons. Coastal creatures time their feeding and breeding to the turning of the tides, and humans have watched and followed the tidal clocks for practical and spiritual calendars. The concept that gravity can move oceans is astonishing. A celestial body so far away causes the water at our feet to rise and fall. If such a gentle gravitational tug can set Earth's massive oceans in motion, What might stronger gravity do on other worlds? We imagined a scale of tides far beyond our familiar beach. And indeed, nature provides a dramatic example. The moons of Jupiter are caught in a gravitational dance far more intense than our moon and Earth. Jupiter, a giant of swirling gas, pulls hard on its moons, and they pull on each other in a complex rhythm. One moon, Io, is so powerfully squeezed and flexed by Jupiter's gravity that its interior rock melts. Io is alive with volcanoes, erupting sulfur and lava, a world literally pulled apart by tides. Just beyond Io orbits Europa, a smaller moon covered in ice. Europa too feels Jupiter's relentless pull, though slightly less violently than Io. Instead of erupting in fire, Europa responds to the tugging in a different way. Its solid surface of ice bends and bows, cracking under the strain. Tidal forces knead Europa's interior like a baker working dough. This flexing generates heat deep inside the moon. Enough heat, scientists believe, to melt ice beneath the crust. In effect, Jupiter's gravity could be warming Europa from within, preventing an internal ocean from freezing solid. The result would be extraordinary. A liquid sea, hidden below an icy shell, kept warm not by sunlight, but by the push and pull of gravity. Before we had evidence of any such ocean, Earth's own tides had already given us a crucial insight. They taught us that water can move in response to a celestial dance, and that even distant forces can shape the fate of a sea. The moon's influence on our tides is a quiet hint that the universe has many ways to keep water in motion. With this lesson in mind, we turned our attention to those distant moons of the outer solar system. Perhaps, under their ice, oceans were sloshing due to the same gravitational music that moves our tides here at home. The first hint that oceans might exist beyond Earth came in the late 1970s from a pair of small spacecraft voyaging through the outer solar system. As Voyager 1 and 2 swept past Jupiter, they sent back images of its moons that astonished scientists. One moon in particular, Europa, showed a surface unlike any we had seen before. Instead of a cratered, ancient landscape like our moon, Europa's face was bright and smooth in many places, crisscrossed by long, dark lines and cracks. These markings looked like veins or the fractured plates of sea ice on Earth's Arctic Ocean. Some of the broken ice fields even seemed to have shifted and rotated, as if floating on something mobile below and refreezing in new positions. To researchers poring over the photos, it was a tantalizing sight, almost a jigsaw puzzle of ice. It hinted that beneath Europa's icy crust, there might be a layer of liquid, allowing the ice to move. In other words, Voyager's camera had given us our first glimpse, albeit indirect, of a hidden alien ocean. For years, this idea remained an exciting possibility. In the 1990s, another mission called Galileo entered orbit around Jupiter and provided an even closer look. Galileo carried instruments that could measure magnetic fields. As it flew by Europa, it detected something unusual, a disturbance in Jupiter's magnetic field around the moon, as if Europa itself were generating a weak magnetic response. The best explanation was a global layer of electrically conductive fluid beneath the surface, likely a salty ocean of water. This was a profound discovery. Though we did not see the water directly, the data strongly suggested that a deep ocean, tens of kilometers thick, lies under Europa's ice shell. Suddenly, the story of Europa as a frozen ball was rewritten. It became a world with two layers, a hard, icy exterior and a concealed ocean inside. We realized that even in the cold darkness far from the sun, A moon could hold an ocean by its own internal heat. Europa was not alone in teasing us with hints of subsurface seas. Galileo's studies of other Jovian moons suggested that Ganymede, the largest moon in the solar system, might also hide a buried ocean beneath a thick crust of ice. Even Callisto, a heavily cratered outer moon of Jupiter, showed signs in its magnetic readings that pointed to a possible subsurface ocean or slushy mantle. Each new piece of evidence painted a picture of the outer solar system as a treasure trove of hidden waters, waiting beneath layers of ice and rock. Then came one of the most dramatic revelations. In 2005, the Cassini spacecraft was touring Saturn and its moons when it flew past tiny Enceladus, a bright, icy moon only about 500 kilometers across. What Cassini found at Enceladus stunned everyone. Towering plumes of water vapor and ice particles erupting from cracks near the moon's south pole. Geysers were blasting out into space, backlit by the sun's rays. It was like discovering a cosmic fountain. There was no doubt about it. Liquid water lay beneath Enceladus's surface, and it was escaping through these fissures. Scientists soon determined that Enceladus harbors a regional sea, or perhaps a global ocean, beneath its icy crust, kept liquid by heat from tidal flexing. This was the first time we actually saw evidence of an extraterrestrial ocean making contact with the space above, in the form of water plumes. We even flew Cassini through the icy spray, tasting the vapor and finding hints of salt and organic molecules. Enceladus had gone from an unassuming little moon to one of the most promising places to look for life, all in a moment, thanks to that shimmering plume of water. Each of these discoveries, the patterned cracks of Europa, the magnetic whispers of hidden seas on Jupiter's moons, and the geysers of Enceladus, gave us a new perspective. Oceans were no longer theoretical possibilities. They were real and present on other worlds, even if concealed. We had glimpsed them through the tools of our ingenuity. The universe was proving to be more water-rich than we once imagined, and the implications for finding life beyond Earth grew more intriguing with every clue. High above, in the dark stretches of the outer solar system, ancient wanderers circle the sun. These are comets, icy relics from the dawn of planets, often called dirty snowballs of space. For most of their lives, they remain invisible, far from the sun's warmth. But every so often, one falls inward towards the light. As a comet approaches the inner solar system, the sun's heat begins to thaw its frozen surface. Gases and dust erupt and envelop the comet in a glowing cloud. A long, shining tail streams out behind it, millions of kilometers long, visible even from Earth as a delicate streak in the night sky. That beautiful tail, spreading across the stars, is essentially water, along with other gases, escaping into space, a cosmic signpost of ice turning to vapor. Comets are messengers of water in more ways than one. Locked within them is water that formed billions of years ago, before Earth itself was fully assembled. In the early chaos of the solar system, countless comets and water-rich asteroids bombarded the young Earth. They delivered much of the water that filled our oceans. Every lake, river, and ocean on our planet may contain molecules that once drifted in a comet's heart. In a sense, the seas of Earth are partly an extraterrestrial gift, the aftermath of countless cosmic ice deliveries. This realization connects us profoundly to the solar system. When we drink a glass of water, or walk by the ocean's edge, we are touching materials as old as the sun, delivered across eons by wandering comets. Our exploration of comets has reinforced just how ubiquitous water is. We have sent probes to chase these icy travelers, like the Rosetta spacecraft that rendezvoused with a comet and even set a lander on its surface. Through such missions, we discovered that comets carry not only water, but also organic molecules, the carbon-rich building blocks of life. In their frozen interiors lie amino acids and other complex chemicals. It's humbling to realize that these drifting snowballs hold the ingredients of life, scattered across the void. When a comet crashes into a planet or a moon, it could plant those ingredients, seeding the raw materials for life's chemistry, wherever conditions become favorable. Comets also remind us that water is not unique to Earth, or even to our solar system. We observe comets around other stars. By the subtle way their tails absorb starlight, indicating they too shed water as vapor. We see the spectral fingerprints of water in distant young planetary systems, suggesting that newborn worlds elsewhere are also swarmed by comets and ice. Water, it appears, is a common thread woven through the cosmos, available almost everywhere if you know how to look. Yet, having water is one thing. Gathering it into a vast, stable ocean is another. Comets show that the ingredients are abundant, but to form a lasting sea requires the right conditions. Still, these cosmic ice messengers give us hope. They prove that the fundamental component for oceans, H2O, is widespread. So as we contemplate oceans on alien worlds, we do so knowing that the universe has plenty of water to go around. The question becomes, where has it collected and remained liquid, creating a haven where life might spark? The journey of water from comets to planets sets the stage for why finding an ocean in space matters so much to us. By now, it's clear that finding an ocean on another world is more than just discovering some water. It's discovering a potential cradle for life. Every drop of liquid water is a tiny potion of possibility. On Earth, life needs water at every turn. It is the medium in which cells swim, where chemistry becomes biology. So when we find a world awash in water, especially liquid water, we cannot help but wonder if life has taken root there too. An ocean provides a vast, continuous environment where life might arise and evolve. Unlike a small oasis or an intermittent puddle, a stable ocean endures through time and across global scales. This makes it one of the most promising settings for life beyond Earth. In our minds, an alien ocean world practically invites speculation about alien fish, microbes, or stranger creatures swimming in its depths, even if in reality any life might be microscopic. Oceans also matter for the stability they confer to a planet or moon. Consider Earth. Our ocean acts as a giant thermostat and life support system. It absorbs heat in the summer and releases it in the winter, smoothing out temperature extremes. It carries warm and cold water around the globe, preventing any one region from becoming inhospitably hot or cold for too long. It dissolves carbon dioxide from the air, helping regulate our climate. Thanks to the oceans, Earth's environment has stayed remarkably steady for millions of years, giving evolution a reliable stage on which to play out the drama of life. If we find an ocean on a distant planet, we suspect that world might likewise enjoy a more stable climate than a dry world, increasing the chances that life could endure and progress. An ocean can also shield and nurture life in ways that a barren surface cannot. Deep beneath an ocean's surface, living organisms are protected from the deadly vacuum of space, harsh stellar radiation, and the shock of meteor impacts. On a world like Europa or Enceladus, a thick cap of ice over the ocean might serve as a sturdy roof, keeping the water below safe from cosmic hazards. This stability and protection mean that even if the surface of a planet or moon is uninhabitable, the ocean below could remain a livable haven. It's a bit like a house with a strong roof through a storm. Life can continue in the basement, even if the outside world is ravaged. This idea has expanded our concept of the habitable zone around stars. We used to think a planet had to be at just the right distance from its sun for liquid water to exist on the surface. Now we realize that tidal heating or internal heat can sustain oceans even far outside those bounds, deep underground. Oceans, in essence, broaden the range of places where life might find a foothold. Beyond their practical benefits, alien oceans captivate us because of the sheer mystery they hold. Humanity has always been fascinated by the unknown, and what could be more unknowable than a sea on a distant world? Even our own oceans on Earth are only partially explored. The deep sea floor, with its strange creatures and sunless black waters, reminds us how alien even Earth can feel. Now imagine an ocean that has evolved entirely separately, under the ice of a foreign moon or beneath the clouds of a far-flung planet. The thought of what might live in those waters, if anything, tickles our imagination. Would life there resemble anything we know? Would it have eyes to see in the darkness, or luminous bodies that glow in perpetual night? Could intelligent beings swim in those hidden seas, never knowing a sky or stars, their entire civilization underwater? These questions belong as much to the realm of dreams as to science, but they are a powerful motivation. Oceans represent the great unknown, holding secrets in their depths. Finding an alien ocean is almost like finding a new realm of existence and a new chapter of nature's story that we have yet to read. In summary, oceans matter in space because they combine all the factors we believe are crucial for a living, dynamic world. They provide water in abundance, a stable environment protected from extremes, and a canvas on which life's complexity can paint itself over time. They also spark our sense of wonder like nothing else. Every confirmed ocean beyond Earth is a promise. The promise of a world that might be alive or could one day be home to life. That promise drives us forward, pushing us to learn more and to explore further, fueled by both scientific curiosity and the timeless allure of the sea. Finding evidence of hidden oceans was just the beginning. Once we knew they existed, the next challenge was to understand them, to chart their extent, depth, and conditions without ever directly seeing them. In a way, it was like mapping a lake on the far side of a wall, using only faint echoes and subtle vibrations. Our spacecraft became the cartographers of these unseen seas, using science and ingenuity as their map-making tools. Imagine a probe flying low over the icy surface of a moon like Europa. To the naked eye, all it sees is a landscape of ridges, cracks, and frozen plains. But the probe carries instruments that can sense the invisible. As it glides through Europa's weak magnetic field, it records a slight oscillation, a telltale sign that a conductive layer of liquid lies below the ice, affecting the magnetic environment. At the same time, the probe's radio signals back to Earth experience tiny delays and shifts as it flies over different regions. These signals reveal subtle variations in gravity, which scientists translate into a picture of the moon's internal structure. A slightly weaker gravitational pull in one area might indicate a thicker layer of low-density water there. By piecing together these clues, we begin to outline the hidden ocean's shape and depth. In essence, we have drawn the first rough map of Europa's internal ocean, without ever seeing a drop of it. Similar techniques have now been applied to multiple worlds. The Galileo spacecraft's data implied Europa's ocean is global, perhaps 100 kilometers deep, beneath an ice shell, only a few kilometers thick. Galileo also hinted that Ganymede has a deep ocean sandwiched between layers of ice, and even Callisto might have a slushy sea locked away. The Cassini probe around Saturn used gravity measurements to confirm that Enceladus's ocean is not just a localized lake feeding its South Pole geysers, but likely a global ocean separating the crust from the core. Cassini also watched Titan, noticing the subtle wobble in Titan's rotation that indicated its icy crust floats atop a liquid layer. An underground ocean tens of kilometers below the surface of that haze-wrapped moon. Piece by piece, flyby by flyby, we have gathered data and drawn conclusions, turning remote measurements into knowledge of alien seas. We now speak of an atlas of ocean worlds in our solar system. This atlas is unlike any conventional map. It exists in scientific papers, computer models, and in artists' imaginations, since we cannot directly photograph these oceans yet. But it's growing richer by the year. We know, for example, that Europa's hidden ocean likely contains more water than all of Earth's oceans combined. Titan's concealed ocean might be mixed with ammonia, an antifreeze that keeps it liquid at frigid temperatures. Enceladus's ocean, sampled through its geysers, appears to be salty and contains organic molecules, hinting at active chemistry. Even distant Pluto, which we once thought to be a frozen rock, has shown signs that it may harbour a subsurface ocean, revealed by the patterns of its surface fractures and the models of its interior. The more we look, the more we realise that oceans may be a common feature in our solar system's outer reaches. To refine these maps, we are preparing new missions armed with advanced tools. Soon, spacecraft will carry ice-penetrating radar to moons like Europa, allowing us to peer beneath the crust, much like a medical scan looking beneath skin. We'll receive the first detailed profiles of how thick the ice is in different regions, and perhaps even detect pockets of water or brine within the shell. Other instruments will listen for tremors and vibrations in the ice, like geologists using seismic waves on Earth to understand the layers below. Every new bit of data will sharpen our image of these alien oceans. It is remarkable how far our understanding has come in such a short time. Not long ago, we had no proof that any ocean existed beyond Earth. Now we have not only found several, but also begun to chart their breadth and depth, using nothing more than distant sensing and human cleverness. These maps of the hidden deep are still rudimentary, more outlines than detailed charts, but they inspire us. They are the first drafts of future exploration, guides that could one day lead a probe or a submersible to the exact spot where an extraterrestrial wave might be waiting to break the silence. Knowing that alien oceans exist is one thing. Venturing to explore them up close is the next great adventure. We stand today at the edge of this uncharted sea, like ancient mariners contemplating a voyage to a new continent. The shores we plan to reach are not on any earthly map. They lie on distant moons and planets, under unfamiliar skies and behind veils of ice. Preparing to explore these strange shores requires both technological innovation and a mindset of wonder, caution, and determination. Our engineers and scientists are already dreaming up ways to send explorers, most likely robotic, into those alien depths. One vision involves a probe that could land on Europa's frozen surface, then slowly melt or drill its way through kilometers of ice. Imagine a mechanical sphere, heated and powerful, boring down for weeks or months, finally breaking through to the dark ocean below. At that moment, it would release a small submersible drone into the water, humanity's first swimmer in an alien sea. That drone might have lights and cameras, perhaps even chemical sensors to sniff out organic molecules or signs of life. It would glide through black waters, beams of light cutting through the gloom, as it examines an environment never before touched by human technology. Designing and building such a probe is an enormous challenge. The crushing pressure in the depths, the unknown terrain under the ice, and the difficulty of communicating through kilometers of ice all pose major hurdles. Yet, step by step, we are working on the technologies that could make it possible. We draw on our experience exploring Earth's deep oceans with robotic submarines and on specialized drills used in Antarctica to reach subglacial lakes. Each test and prototype brings us closer to the day we might pierce the icy ceiling of an alien sea and send a mechanical explorer swimming into its darkness. In the nearer term, there are plans to return to these ocean worlds with probes that stay above the water, but tell us more about it. The Europa Clipper mission, for example, will orbit Jupiter and make dozens of close flybys of Europa, each time using its suite of instruments to scan the ice, gauge the magnetic and gravity fields, and perhaps even sample any water vapor plumes venting from the surface. Concepts for an Enceladus mission would involve flying through its geyser plumes with advanced detectors, essentially tasting the spray for signs of organic compounds or even microbial life. On Titan, a different kind of ocean exploration is envisioned. A submarine could one day be launched into Titan's largest methane lake, Kraken Mare navigating its liquid hydrocarbons to study an otherworldly sea under an orange sky. Each of these plans is a stepping stone, meant to gradually increase our understanding before we attempt the more audacious goal of entering a subsurface ocean itself. By learning more about the ice crusts, the water chemistry, and the potential energy sources that might support life, such as hydrothermal vents on ocean floors, we'll be better prepared to design the ultimate missions that dive into the waters. As we prepare to explore, we also must consider how to do so responsibly. These oceans have been sealed away for geologic time, untouched by earthly life. If some native ecosystem exists in them, it has a right to remain pristine and unharmed by our intrusion. We have a responsibility to avoid contaminating those waters with microbes from Earth. So any probe that might contact the water will need to be sterilized to an incredibly high standard. We also have to be careful in how we operate. For example, if we only melt through the ice and peer in, we might minimize disturbance to a potential ecosystem. The philosophy of planetary protection guides us to explore, but gently, and with respect for whatever we may find. The human element of this endeavor is just as significant. Undertaking a mission to explore an alien ocean demands patience and long-term commitment. It might take a decade or more just to develop and launch the spacecraft, and several more years for it to travel across space to its destination. Many of the engineers and scientists involved will pour their careers into a project that may only fully bear fruit for the next generation. This continuity of purpose, planting trees under whose shade one may never sit, is a hallmark of deep exploration. It reminds us that discovery isn't just a momentary triumph, but a legacy built over many years. There's also a sense of humility we carry with us. We know we might be stepping into the truly unknown. All our theories and models might only partially prepare us for what an alien ocean will actually be like. We have to be ready for surprises, perhaps even confounding ones. Maybe the water will be full of exotic chemistry, unlike anything on Earth's oceans. Or maybe we will find that life is absent where we expected it, teaching us that not every ocean will automatically teem with living things. Whatever the outcome, we will learn something profound about the nature of worlds beyond our own. Picture the moment, someday in the future, when our robotic explorer finally sends back the first images from an alien ocean. Perhaps its camera lights will reveal a forest of mineral chimneys on the ocean floor, akin to the hydrothermal vents on Earth, with strange organisms clustered around them. Or maybe the water will appear eerily empty, a silent abyss of rock and ice. Even in that quiet scene, there would be profound beauty and meaning. The very act of reaching that far, of dipping our mechanical hand into an extraterrestrial sea, will be an awe-inspiring milestone for humanity. In that instant, the distance between us and that distant world will collapse, and we will become participants in its environment, not just distant observers. Our journey so far, from the familiar waves of Earth to the hidden seas of nearby moons, has shown us that oceans can exist in the most surprising places. It has changed the way we see our solar system, transforming many of those distant points of light into dynamic worlds with their own cycles and stories. And yet, this is only the beginning of a much longer voyage. With the knowledge we've gained here at home, we now look beyond our sun. Around countless other stars, planets circle in vast cosmic oceans of their own. Some of those planets may be water-rich, even entirely covered in global oceans. Others might hide liquid lakes beneath surfaces of ice or clouds. They beckon to us through our telescopes and our models. Equipped with what we've learned about finding and studying oceans in our solar system, we prepare to seek out the seas under distant suns. Our imaginations sail ahead to worlds we have yet to see, driven by the enduring hope that on some far-off shore, life is watching its own sunrise over alien waters, waiting to be discovered. The cosmos seems to have a favourite between matter and its ghostly twin, antimatter. Shortly after the Big Bang, particles of matter and antimatter should have been created in equal numbers, destined to annihilate each other in brilliant bursts of energy. Yet, as the eons unfolded, almost all the antimatter vanished, leaving a universe dominated by matter. Every star we see, every planet, every atom in our bodies is made of matter, a triumph of matter over antimatter. Why did nature choose matter? It's one of the most perplexing asymmetries in science. If the laws of physics treat matter and antimatter nearly the same, one would expect a perfect balance, with mutual destruction leaving behind nothing but light. Instead, for every billion matter-antimatter pairs that annihilated in the early universe, a tiny bit of matter, perhaps just one particle in that billion, survived. That tiny imbalance is what built our entire material cosmos. Somewhere in the microphysics of the early universe, matter gained a slight edge over antimatter, and we are the living proof. Physicists suspect that the secret lies in subtle differences in how matter and antimatter behave. In the laboratory, we've observed a phenomenon called CP violation, where certain unstable particles decay in a way that favours matter over antimatter by a minuscule amount. It's as if the mirror image symmetry between matter and antimatter has a tiny crack. These effects, first seen in particles called kaons and more recently in B mesons, show that nature isn't perfectly impartial after all. However, the known CP violations in particle physics are far too small to explain the enormous bias towards matter in the universe. It's like finding a slight wobble in a coin that usually comes up heads only 50.1% of the time, yet somehow, in a grand cosmic coin toss, heads came up virtually every time. There must be additional, as yet unseen biases or events that tipped the scales during the universe's first moments. Scientists have proposed various ideas for how the matter-antimatter imbalance came to be. One idea is that in the extreme conditions of the early universe, exotic heavy particles, predicted by theories extending beyond the standard model, might have decayed in ways that produced more matter than antimatter. As the universe cooled and these heavy particles vanished, they would have left behind an excess of matter. Another idea involves neutrinos, the nearly invisible particles that abundantly zip through us. If neutrinos are their own antiparticles and exhibit CP violation in their oscillations, they might have sown the seeds of matter's dominance through a mechanism called leptogenesis, a subtle bookkeeping swap that ultimately produces more protons than antiprotons. These hypotheses are bold and complex, and physicists around the world are devising experiments to test them, from measuring CP violation in neutrinos to studying the properties of antimatter atoms with exquisite precision. Each experiment is essentially asking the universe, where did the antimatter go, and why are we made of what's left? The triumph of matter over antimatter is not just an esoteric puzzle, it's the reason we are here to puzzle over it at all. If nature hadn't favored matter just enough, the galaxies would contain no solid worlds or living beings, only radiation filling an eternal void. This realization gives a poignant twist to our understanding of existence. The universe as we know it is built on a tiny imperfection, a deviation from perfect symmetry. Unraveling that imperfection is a top priority in cosmology and high-energy physics. New data from particle accelerators and deep space observations will help us piece together the story. We may find new particles or forces that explain the cosmic preference for matter, or we may discover that the imbalance arose from interactions in the fiery infant universe we have yet to imagine. Until then, the asymmetry stands as a reminder of how much we owe to the universe's little quirks. From the smallest atom in our body to the grandest galaxy, all of material existence is a monument to an ancient cosmic preference that we are only beginning to understand. If our universe holds hidden dimensions, they are hidden extraordinarily well. For centuries, we have known only 3 dimensions of space: length, width, height, along with 1 dimension of time. Everything we experience unfolds in this 3+1 dimensional stage. But modern theories in physics tantalize us with the possibility that this stage is not the whole theatre of reality. There could be additional spatial dimensions curled up beyond our perception, like secret rooms tucked behind the walls of our observable world. In these unseen dimensions, the fundamental forces and particles might take on a more elegant form, potentially unlocking answers to deep questions. The idea of extra dimensions isn't mere science fiction. It has serious motivation in physics. Over a century ago, the mathematician Theodore Kaluza proposed that if you imagine a 5th dimension beyond the usual 4, you could unify gravity and electromagnetism in one theoretical framework. Einstein and others were intrigued. It was as if adding a hidden backroom allowed 2 separate forces to meet and become one. In the late 20th century, the necessity for extra dimensions became even more pronounced with the rise of string theory. String theory posits that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings of energy. Remarkably, the mathematics of string theory only works consistently if there are more than 4 dimensions. In fact, it requires around 10 spatial dimensions for a total of 11 spacetime dimensions in its most symmetric form. These extra dimensions, according to the theory, are compactified, curled up into tiny shapes, like microscopic loops or complex curving surfaces known as Calabi-Yau manifolds. They are so small that we don't notice them in everyday life, just as an ant crawling on a thin wire might not realize it can loop around the wire's tiny circumference. What would it mean if such hidden dimensions exist? It could mean that forces like gravity, which in our familiar 3 dimensions are feeble on the scale of particles, might actually spread through more dimensions than we realize, diluting their apparent strength. Some physicists have suggested that the reason gravity is so much weaker than the other forces, allowing us to jump despite the pull of an entire planet, is that gravity leaks into these extra dimensions, while other forces do not. In one imaginative scenario, our observable universe might be like a 3-dimensional membrane, or brain, floating in a higher dimensional space. All the particles and forces we know, except gravity, might be stuck to this brain, unable to leave it, which is why we don't see the other dimensions. Gravity, however, emanates from the fabric of spacetime itself and might seep into the greater dimensional space, explaining its relative weakness and offering a chance to detect other dimensions by their gravitational influence. Scientists have been searching for any sign of extra dimensions. In particle colliders, like the Large Hadron Collider, researchers look for energy seemingly disappearing during particle collisions, which could indicate that some of that energy has leaked away into higher dimensions. They also look for the production of tiny, higher dimensional versions of particles or brief microscopic black holes that might flicker into existence if the fabric of space-time has more folds than we thought. So far, no conclusive evidence has emerged. Gravity has also been tested at very small scales in laboratory experiments to see if it deviates from Newton's law at sub-millimeter distances, a possible sign that gravity is feeling the effects of extra dimensions at that scale. Again, within experimental precision, no deviation has been found yet. The extra dimensions, if they exist, remain frustratingly hidden. Despite the lack of evidence, the allure of unseen dimensions remains strong because of the elegant solutions they offer to pressing puzzles. They could provide a natural home for the unification of forces, the long-sought theory that joins gravity with quantum mechanics. In the mathematical architecture of string theory, for example, the geometry of the compactified dimensions determines the types of particles and forces we observe. The hope is that one day, by understanding this geometry, we could deduce why our universe has the properties it does, such as the charges of particles and the strengths of forces. Imagine unlocking a geometric code that explains why electrons have their particular mass, or why the strong force is just so strong. Extra dimensions promise such a code, written in the shape of the unseen. For now, these additional dimensions remain a speculative but compelling possibility. They remind us that our perception of space might be limited. We could be like insects crawling on a vast 3D surface, unaware of the broader landscape around us. If and when we find proof of extra dimensions, it would revolutionize our understanding of reality. It would mean that the cosmos has more directions to explore than we ever imagined, and that our journey through the universe has been confined to a small subspace of a much grander structure. Until that day, we continue to probe and listen for any whispers from these hidden realms, keeping an open mind that the true map of existence may have more axes than our senses can currently draw. The standard model of particle physics is a spectacular achievement, and yet a work in progress. Like a nearly completed puzzle, it shows us a vivid picture of the fundamental particles and forces that compose reality. With the discovery of the Higgs boson in 2012, the last predicted piece of the standard model fell into place, confirming a mechanism by which particles gain mass. We now have a robust theory describing electrons, quarks, photons, gluons, and more, all interacting in ways that have been confirmed to astonishing precision by experiments. It is a triumph of human ingenuity that such a theory exists and works so well. But despite its success, the Standard Model leaves profound questions unanswered, cracks at the foundations that hint at a deeper, more complete theory waiting to be discovered. One glaring omission in the Standard Model is gravity. The model does not include the force of gravity at all, focusing only on three forces: electromagnetism and the strong and weak nuclear forces. A true Standard Model of all physics would need to incorporate gravity, perhaps through a hypothesized particle called the graviton, but attempts to quantize gravity so far have led to theoretical difficulties. This means our Standard Model is, strictly speaking, a partial model of reality. Beyond gravity, there are other puzzles. For example, the Standard Model originally assumed that neutrinos, ghostly, nearly massless particles, had zero mass. We now know neutrinos do have a tiny mass and oscillate between identities, which means the model needs an extension to accommodate this finding. What mechanism gives neutrinos mass? Is it another kind of Higgs-like field, or something more exotic? We don't yet know, and it's a window into physics beyond the Standard Model. There's also the fact that 95% of the content of the universe is not described by the Standard Model at all. Astronomers and cosmologists have compelling evidence that about 27% of the universe is dark matter, some kind of matter that doesn't emit or absorb light and isn't made of any known particles in the Standard Model. Another 68% or so is dark energy, an even more mysterious phenomenon driving the accelerated expansion of the universe. The Standard Model, comprising all known particles, accounts for only about 5% of the universe's mass energy, the normal matter that shines in stars or forms us. This is a humbling gap in our understanding. Identifying the nature of dark matter is one of the foremost goals of modern physics. Many suspect it could be a new particle outside the Standard Model, perhaps a WIMP, weakly interacting massive particle, or an axion, a hypothetical, lightweight particle. But despite extensive searches in deep underground detectors and powerful accelerators, no confirmed dark matter particle has shown itself yet. Then there are the more subtle riddles that suggest the Standard Model is incomplete. One is the question of why particles have the masses and forces they do. The model contains a list of numbers: masses of quarks and leptons, the strengths of forces, mixing angles between particle families, that are measured experimentally, but not explained by the theory. They are like dials, set to very specific values, and we have no underlying principle, yet, that determines those settings. Why is the electron about 2,000 times lighter than the proton? Why are there exactly 3 generations of quarks and leptons, grouping particles into trios of increasing mass? The Standard Model doesn't say. Many physicists suspect that there is a deeper symmetry or principle, perhaps manifest at extremely high energies or in the early universe, that fixes these values, and that what we see now is a low energy reflection of that principle, with the symmetries broken. Grand unified theories, GUTS, for instance, envision that at mind-boggling temperatures, all 3 forces, except gravity, merge into one, and the distinctions between quarks and leptons blur. Such unification models often predict new particles, or even additional forces, some of which might leave subtle fingerprints, such as the very slow decay of protons, or the existence of magnetic monopoles, hypothetical north or south only magnetic charges. Experiments have not found these phenomena, putting strict limits on the ideas, but not ruling them out completely. Moreover, intriguing anomalies keep cropping up at the edges of our experiments. There have been long-standing tensions, for example, in the measured magnetic moment of the muon. The muon is a heavier cousin of the electron. The muon G2 experiment recently confirmed a tiny discrepancy between the standard model prediction and the observed behavior of muons in a magnetic field. This could be a hint that unknown virtual particles, possibly from beyond the standard model, are influencing the muon's properties. Similarly, some experiments with particles called B mesons have observed decays that don't perfectly match standard model expectations, hinting that perhaps a new force or interaction might be at play. While these anomalies are not yet definitive evidence of new physics, they certainly stoke the excitement that we are on the verge of expanding our model. The history of physics has often been one of unexpected experimental results, leading to revolutionary theories. The unfinished business of the standard model is a reminder that every theory, no matter how elegant and successful, resides within a larger context of ignorance. We stand today with a cohesive picture of particles and forces that successfully explains so much, and yet we know it must be part of an unfinished tapestry. The coming years and decades hold the promise of new discoveries. Perhaps the capture of dark matter particles in our detectors, or the creation of strange new particles at upgraded colliders, or the revelation of tiny symmetry violations in precision experiments that tell of new fields and forces. With each new clue, we will refine our understanding, piece by piece, towards a more complete model of the fundamental workings of nature. We don't know if the ultimate theory will arrive in a neat aha moment or in a slow accumulation of insights, but we do know that the standard model is not the final story. Beyond it lies a frontier of potential breakthroughs, waiting for us to venture further and continue the quest that began when humanity first wondered what the world is made of. High above us, in the heart of exploding stars and the collisions of ultra-dense remnants, nature forges gold, uranium, and all the heavy elements that enrich the cosmos. This cosmic alchemy, the process by which the elements are created, is a tale that science has been gradually unveiling. We have traced much of it. Lighter elements like hydrogen and helium were formed in the primordial fireball of the Big Bang, while a whole range of heavier elements up to iron are continuously cooked in the cores of stars through nuclear fusion. But the creation of elements heavier than iron requires more violent foundries. These elements, the gold in our jewelry, the iodine in our thyroids, the uranium deep in Earth's rocks, are formed in rare, cataclysmic settings that push matter to extremes. And although we have identified some of these settings, like supernovae and neutron star mergers, we still have unanswered questions about the precise origins and abundances of the heaviest elements. In the life of a massive star, a dramatic full stop occurs when its core fills up with iron. Iron cannot release energy by fusion. Instead, any further fusion would consume energy. So, when a star builds an iron core, it's akin to a fire running out of fuel. What follows is a supernova explosion. The core collapses under gravity and then rebounds, blowing the star's outer layers into space. These fleeting moments of fury create conditions intense enough to synthesize elements heavier than iron. Through what's known as the rapid neutron capture process, or R process, atomic nuclei in the star's wreckage are bombarded by a flood of neutrons. Nuclei rapidly absorb neutrons faster than they can decay, climbing the periodic table to build extremely heavy elements. When the chaos settles, those nuclei decay into more stable forms, becoming things like silver, gold, platinum, xenon, and uranium. For a long time, scientists theorized that supernovae were prime sites of the R process. Indeed, certain types of supernovae, especially those with fast-spinning, highly magnetized neutron star remnants called magnetorotational supernova, are still considered potential heavy element factories. Yet, Detailed models of ordinary supernova explosions have sometimes struggled to produce the heaviest elements in the needed amounts, raising the question of whether something even rarer might be responsible. A breakthrough in this age-old mystery came only recently. In 2017, astronomers observed for the first time the merger of two neutron stars, detected in both gravitational waves and electromagnetic light. Neutron stars are the ultra-dense cores left behind by supernovae, packing more mass than our Sun into a ball only tens of kilometers across. When two neutron stars spiral together and collide, the conditions are almost unimaginably extreme. Torrents of neutrons, incredible temperatures and pressures, and huge ejections of neutron-rich matter spray out into space. The 2017 event, named GW170817, produced an electromagnetic afterglow called a kilonova, whose light carried spectral fingerprints of freshly forged heavy elements, exactly what theory predicted an R process would do. It was as if nature had lit a cosmic furnace, and we caught it in the act of minting gold and other treasures. This observation has strongly pointed to neutron star mergers as a major, if not dominant, source of the universe's heaviest elements. In fact, some studies suggest that a single neutron star collision can produce an Earth's mass worth of gold. However, even with that discovery, puzzles remain. We're still trying to quantify how much each source contributes to the cosmic inventory of heavy elements. Neutron star mergers are rare events, perhaps more rare than supernovae. So could they alone account for the abundance of gold and platinum we see in old stars and in our solar system? Some evidence from stellar archaeology, studying ancient stars that formed early in the galaxy's history, indicates that not all heavy elements can be solely attributed to neutron star mergers. Perhaps some exotic types of supernovae are also contributors. The relative roles of different processes, the R process in neutron star mergers versus rare supernovae, and the slower S process, slow neutron capture, in aging giant stars that produces elements like strontium, barium, and lead, are still being unraveled. Each heavy element likely has a different story. For instance, most of the iodine in our bodies probably came from exploding massive stars, while most of the gold in our jewelry might have come from a neutron star collision billions of years before our Sun formed. Moreover, questions persist about the upper limits of the periodic table. In laboratories on Earth, we have managed to create elements beyond uranium, like plutonium, americium, and so on, up to element 118, oganesson. But these are all unstable and decay quickly. Is there an island of stability of super heavy elements that could perhaps exist naturally under extreme conditions? Could, say, an element with around 120 or 126 protons have a comparatively long lifetime? If so, might nature be making any of these in the colossal events we've been discussing? It's speculative, but scientists have wondered if neutron star mergers or supernovae might briefly create nuclei in this hypothesized island of stability, and whether any might survive long enough to be detected. So far, we have no evidence of naturally occurring stable superheavy elements, but the quest to extend the periodic table, both in accelerators and in cosmic debris, continues. In essence, the saga of the elements is one of continuous discovery and surprise. We have gone from ancient alchemists dreaming of turning lead into gold, to modern scientists realizing that the universe does this transmutation routinely in its violent deaths and collisions. We are ourselves made of this stellar alchemy. The iron in our blood was once the ash of a star's fusion, and the calcium in our bones likely came from an exploding star eons ago. Every heavy element carries the story of a cosmic cataclysm. As we refine our models of supernovae and simulate neutron star mergers in greater detail, we hope to answer lingering questions. Exactly which stars produce Which share of the heavy elements? How do those elements disperse and eventually seed new solar systems like our own? The answers will complete the story of matter's journey from the Big Bang to the periodic table we know. And with each answer, we gain not only knowledge, but a deeper connection to the cosmos, understanding how the glittering gold and the life-enabling iodine, the uranium and the rare earth metals, all found their way from the hearts of ancient stars to our tiny corner of the universe. On a late afternoon, you might watch sunlight dance on the surface of the ocean and notice patterns of shimmering waves that never repeat the same way twice. The air above the water swirls in unpredictable gusts. High in the sky, clouds form filigree whirls and branching puffs that seem at once random and strangely familiar. These are the hallmarks of chaos and turbulence, phenomena that pervade the natural world and yet defy complete understanding. Within their apparent randomness lies a hidden tapestry of order, a subtle geometry of fractals, and a rigid scaffold of physical laws that we are only beginning to discern. The patterns in chaos hint that even in complete disorder, nature often preserves a kind of symmetry or self-similarity, teasing us with the idea that if we look deeply enough, we might find rhyme and reason in what seems like pure caprice. Turbulence. The word itself evokes the violent, unpredictable motion of fluids, from water flowing in a rocky brook to the whirling atmosphere of Jupiter. It is said that fully understanding turbulence is one of the last great unsolved problems of classical physics. The equations that govern fluid flow, the Navier-Stokes equations, are well known, yet their solutions in the turbulent regime are maddeningly complex. When flow is smooth, laminar, as in a gentle streamlining of air around a wing, we can predict it reliably. But turn up the speed or scale, and laminar flow can erupt into eddies within eddies, big swirls that spawn smaller swirls, which spawn even smaller ones, in a cascade that seems to dissolve orderly motion into randomness. The challenge of turbulence is that these swirls span a vast range of sizes and times, all interacting. It's like trying to track the dance of millions of dancers of different sizes, all influencing one another in a grand, chaotic ballroom. No supercomputer today can brute force calculate every eddy in a large turbulent system like the global atmosphere. The problem is just too vast. And yet, engineers and physicists persist, because unlocking turbulence would have immense practical and theoretical payoff. We'd better predict the weather and climate, design more efficient vehicles, perhaps even understand the dynamics of galaxies and star-forming clouds. Amid this seeming chaos, scientists have discovered that turbulence is not simply random. It has structure. In the 20th century, mathematician Benoit Mandelbrot and others introduced the concept of fractals, shapes or patterns that exhibit self-similarity across scales. Mandelbrot famously examined the question, "How long is the coast of Britain?" and showed that the answer depends on the scale of measurement. The smaller your measuring stick, the more craggy details of coastline you capture, and the longer the coast seems. Coastlines, cloud boundaries, mountain ranges, blood vessels, broccoli romanesco, all show fractal characteristics. Likewise, turbulent flows have fractal aspects. The eddies in a turbulent fluid often form filamentary and sheet-like structures that, when visualized, reveal intricate, repeating patterns. A satellite image of a rotating cyclone can look uncannily like the spiral pattern in a small dish of stirred water, or the swirl of cream in coffee. This self-similarity hints at underlying laws. Indeed, the Russian scientist Andrei Kolmogorov in the 1940s developed a theory of turbulence that describes how energy cascades from large eddies to ever smaller ones in a statistical manner. Kolmogorov's scaling laws do not give us a precise map of each eddy, but they do tell us, for example, how the average velocity differences between 2 points in a turbulent fluid depend on their separation. It's a kind of order amidst chaos, a statistical order. Even in systems that are deterministic and simple in their rules, chaos can emerge. The classic example is the butterfly effect, articulated by meteorologist Edward Lorenz. He discovered that a simple set of equations modeling convection in the atmosphere had solutions that were highly sensitive to initial conditions. Two almost identical starting states would diverge rapidly into very different outcomes. This sensitivity, the notion that a butterfly flapping its wings in Brazil could, through a long chain of amplifications, influence the formation of a tornado weeks later in Texas, underscores why weather prediction beyond a week or two becomes nearly impossible. Yet, Lorenz's equations didn't produce truly random behavior. They traced a peculiar structure in their abstract state space, a shape now known as the Lorenz attractor, which is a kind of fractal. If you plot the chaotic motion of Lorenz's system, it doesn't fill space uniformly. It meanders around in a pattern that looks like the wings of a butterfly. Chaos, in this sense, inhabits a space between randomness and order. It is unpredictable in detail, but not without pattern. This realization has profound implications. It means that within our most unpredictable systems, we might find handles for understanding. We may never forecast the exact path of each molecule in a turbulent puff of smoke, but we can predict the statistical spread of that puff. We can't predict exactly when the next big stock market fluctuation will occur, another famously chaotic system, but we can notice patterns in the fluctuation's magnitudes and frequencies, sometimes described by power laws or fractal dimensions. And where patterns can be recognized, insights can follow. By recognizing the fractal nature of certain patterns in the human heart's rhythm. For example, doctors have learned to identify early warning signs of cardiac chaos that can lead to fibrillation. Randomness itself remains a deep topic. In the quantum world, we encounter what appears to be true randomness, the precise moment when a given radioactive atom will decay, or the outcome of a single quantum measurement, cannot be predicted, only described probabilistically. Is there pattern hidden even in that quantum randomness, or is it irreducible, fundamental chance? Most physicists lean toward the latter, but philosophical questions linger. Perhaps at some deeper level, maybe in a multiverse of many outcomes, or via variables we cannot access, there is an order of which we are ignorant. In any case, from the roll of dice to the noise of thermal motion, randomness, in the macroscopic sense, often carries statistical fingerprints, like the familiar bell curve distribution of averages, or the 1/f noise seen in everything from music to DNA sequences, where fluctuations have a characteristic spectrum. In the swirl of a turbulent waterfall and the branching of lightning bolts, in the rhythm of dripping faucets and the jagged graphs of earthquake intervals, nature demonstrates a fondness for patterns that transcend scale and category. These patterns hint that chaos is not the enemy of understanding, but rather a frontier of it. We have begun to learn the language of chaos, a language of fractals, strange attractors, and non-linear dynamics. But there is so much more to decode. Turbulence, for example, still defies a complete analytic solution. The Clay Mathematics Institute even offered a $1 million prize for a full theory of Navier-Stokes equations that would encompass turbulence. As of yet, it remains unclaimed. And so, we end this part of our journey contemplating a beautiful paradox: the order in disorder. We've seen how the universe's greatest unanswered questions often live in the borderlands between the known and the unknown, the predictable and the unpredictable, from the elegant arcs of planetary motion to the jittery dance of molecules in a gas, from the cosmic to the microscopic. Patterns and mysteries intertwine. Our exploration continues, ever forward, propelled by curiosity. Even as we've sifted insight from symmetry and wrestled with paradox, there are always new edges of knowledge coming into view. With calm wonder, we venture onward into the next chapter of mysteries, carrying with us the humbling recognition that the universe has far more intricate stories yet to tell. Stories we are privileged to listen for, question, and gradually understand as we stand at the edge of knowledge, peering into the infinite unknown. On the surface of a moon circling Uranus, the sunlight is a pale, distant gleam, only a few % as bright as at Earth. Here in the far reaches of the solar system, an eerie blue-green giant planet casts a faint glow on its family of moons. In the cold and dimness around Uranus, one might assume nothing but frozen silence reigns. Yet even in this frigid twilight, there are intriguing signs that liquid water may lurk unseen beneath the ice of some Uranian moons. On the surface of a moon circling Uranus, the sky is a strange deep black, even at noon, with the sun only a small brilliant point far away. The ice underfoot glitters faintly with a blue-green tint, illuminated by the giant globe of Uranus hanging overhead. The planet's aquamarine clouds cast a dim, eerie glow across the landscape. In this perpetual twilight, one might feel that warmth and daylight are worlds away, and they are. Yet beneath the frozen ground, warmth may still linger from an ocean below. Uranus's faint rings might shimmer above the horizon, and perhaps other moons would appear as slowly moving stars in the sky. In this faraway place, warmth from the sun is almost negligible, yet an explorer might find that the ground beneath holds a hidden warmth of its own. Miranda, one of Uranus's smaller moons, reveals itself as a world of strange, patchwork terrain. Voyager 2 images reveal a surface seemingly pieced together from mismatched fragments, cliffs, grooves, and jumbled regions stitched together like a cosmic quilt. Towering scarps and chevron-shaped ridges scar its face, evidence of internal forces that once reshaped this tiny moon. Scientists believe that long ago, Miranda was squeezed and stretched by gravitational tugs from Uranus and neighboring moons, warming its interior. In that warm interval, it may have harbored a deep subsurface ocean sloshing beneath an icy crust. Such an ocean could have been so large that it filled nearly half of Miranda's volume, an astonishing thought for a moon barely 470 kilometers across. Over time, the gravitational dance slowed, and Miranda's tidal heating waned, allowing the moon to cool. But even now, Miranda's cracked and contorted surface hints that the cooling is not complete. If all of its internal water had frozen solid, the little moon might have split open with enormous fractures, scars we do not see. That absence of global fissures leaves scientists to wonder if some remnant of Miranda's ancient sea still survives, locked away under the ice. It is a tantalizing possibility, a quiet reservoir of liquid water, lingering against all odds in a world so small and so far from the sun. Ariel, a larger sister moon of Miranda, also whispers of hidden water. Ariel's surface is etched with long canyons and crisscrossing grooves, as if giant claws raked across its icy plains. Between these gashes lie smoother regions that look like frozen flows, places where water-rich icy slush may have once oozed out and solidified on the surface. Such features suggest that Ariel experienced cryovolcanism, a form of ice volcanism driven by heat inside the moon. Unlike Miranda's chaotic patchwork, Ariel's signs of activity seem more widespread and uniform, hinting at a world that may have remained geologically active more recently. Intriguingly, astronomers have found unexpected chemicals coating Ariel's frosty surface. A significant layer of carbon dioxide ice lies on one side of the moon, and even traces of carbon monoxide have been detected there. Under Uranus's feeble sunlight, these volatile ices should not endure. They ought to evaporate into space unless something keeps replacing them. The presence of these fragile gases suggests they are being fed from within, perhaps by occasional geysers or leaks from an underground reservoir. Scientists speculate that a subsurface ocean could be releasing carbon-rich gases through cracks in Ariel's crust, which then freeze out as frost on the surface. Even more enticing, hints of minerals like carbonates have been observed, substances that form only when liquid water has long contact with rock. All these clues paint Ariel as a likely ocean world, or at least a moon that harboured an ocean in its recent past. A world still gently breathing gases, and maybe even fluids from its interior. It is remarkable to imagine these moons, so distant from the sun, keeping oceans alive under their shells of ice. At Uranus's orbit, warmth from sunlight is scarce. The environment is colder than any winter on Earth could fathom. Yet Miranda and Ariel have shown that internal heat can blossom even here, creating oases of liquid water in the most unlikely of places. They remind us that an ocean world need not lie in the sun's golden warmth. It can exist in the deep cold, lit by starlight and sustained by heat from within. And Uranus's other large moons, Umbriel, Titania, and Oberon, are not to be forgotten. Voyager's brief visit revealed hints of smooth patches and subtle colorations on these moons, clues that suggest past geologic resurfacing events on those distant satellites. Recent analyses imply that Titania and Oberon, the largest of Uranus's moons, could be insulated enough to retain internal oceans of their own. In fact, those buried oceans might even be relatively warm, perhaps warm enough to raise the tantalizing question of whether they could support life, if any microbes ever found their way into those dark seas. We still know very little about these moons beyond a few images, but the possibility that all 5 of Uranus's major moons hide oceans beneath their crusts has transformed our understanding of this once neglected planet. Uranus, viewed from Earth as a small bluish disk, may actually be accompanied by a whole family of ocean worlds. It is like a miniature solar system of hidden seas waiting to be explored. This revelation suggests that Uranus deserves much more attention than it has received, for its moons might hold keys to understanding ocean worlds. Deeper into the outer solar system, the planet Neptune comes into view, a distant blue giant encircled by thin rings and faint bands of clouds. Far colder and darker than Uranus, Neptune guards a remarkable moon named Triton. Triton is an oddity. It travels around Neptune in the opposite direction of the planet's rotation, as if it were a wandering soul captured long ago. This backward orbit hints that Triton was not born alongside Neptune, but instead came from afar, perhaps an ocean world from the Kuiper Belt, now adopted as Neptune's own. When Voyager 2 flew past Triton in 1989, it revealed a surprisingly active landscape, despite surface temperatures near -235 degrees Celsius. Images showed vast frozen plains with a young, lightly cratered surface, implying that geologic processes have erased many ancient scars. Most astonishing were the geysers, thin plumes of material shooting skyward from Triton's south polar region. Dark streaks stained the ice near the South Pole, marks left where these plumes fell back to the surface, clear evidence of ongoing eruptions in that frozen environment. These geysers were found to spurt mainly nitrogen gas, the same substance that makes up most of Triton's whisper-thin atmosphere, carrying fine, dark particles that dust the surrounding ice. To witness active plumes on so remote a moon was extraordinary. At the time, Triton became only the third known world, after Earth and Jupiter's fiery moon Io, where eruptions were directly seen. In Neptune's feeble daylight, it seemed incredible that solar warmth alone could drive such geysers, hinting that another energy source must lie hidden below Triton's surface. In spite of Triton's ultra-thin air, only about 1/70,000th the pressure of Earth's atmosphere, gentle winds can still waft the plume material sideways, painting those dark streaks across the icy ground. Scientists suspect that something more than faint sunlight is at work beneath Triton's crust. The moon's past holds a dramatic story. After Triton was captured by Neptune's gravity eons ago, it likely went through a period of intense internal stress and heating. As Triton's initially eccentric orbit gradually became circular around Neptune, the friction deep inside the moon would have melted much of its interior. In effect, Triton was reborn with an internal ocean beneath its surface, its icy crust floating atop a layer of liquid. Over time, that ocean began to refreeze, but perhaps not completely before the internal heat source waned. Even now, the moon's activity hints at warmth from within. Those nitrogen plumes might be fueled by residual heat still escaping from Triton's core, or by pockets of liquid beneath the ice that occasionally find a path to burst out. Some scientists propose that Triton's geysers are true cryovolcanoes, not merely ice warmed by the distant sun, but jets driven by internal energy that carry water and ammonia along with nitrogen gas. Triton's very landscape reinforces this idea. Its smooth young plains and strange cantaloupe terrain bear few impact craters, indicating the surface has been renewed in the recent geologic past. Taken together, these clues suggest that a substantial ocean still slumbers under Triton's frozen crust, making it a likely ocean world, despite orbiting so far from the Sun. Triton stands as Neptune's icy, ocean-bearing child in all but name, a dynamic alien world so far from the Sun that noon there looks like deep twilight here on Earth. Its active geysers and possible seas beneath the crust show that even in the dimmest outskirts of the solar system, a moon can surprise us with geological vitality. As our journey carries us beyond Neptune, we realize that Triton is not unique. Other worlds farther out may also conceal liquid water, waiting for us to uncover their secrets out in the outer darkness. If one could stand on Triton's surface, the sun would be barely more than the brightest star in a twilight sky. The horizon would be bathed in a pale, peach-colored light, reflecting off nitrogen frost. In the distance, one might glimpse a dark geyser plume slowly climbing up into the nearly non-existent atmosphere, carried sideways by gentle winds before snowing back down as dark smudges on the ice. Above it all, the immense blue orb of Neptune would loom, its presence dominating the sky and reminding any traveller that Triton, though far from the Sun, is still connected to a larger dance around a distant giant. The air is so cold, around -235 degrees Celsius, that each breath would instantly freeze, but at the same time, the ground below is being reshaped by forces from within. Beyond Neptune's orbit lies a vast expanse of darkness and ice known as the Kuiper Belt. This distant region, stretching tens of billions of kilometers from the Sun, is like a deep freeze filled with countless ancient remnants of the solar system's formation. Here the Sun is just a tiny, cold star, and the worlds that circle in this outer belt receive only a faint whisper of its warmth. For a long time, scientists imagined these objects to be inert balls of ice and rock, cosmic leftovers frozen solid in the outer dark. This view began to change as we discovered more about Pluto and its neighbours. Far from being static chunks of ice, some of these distant worlds show hints of internal activity. Pluto, once deemed a frigid dead sphere, revealed a surprisingly youthful and varied surface when visited by a spacecraft, suggesting heat and motion beneath its crust. If Pluto could possess an underground ocean in such cold conditions, could the same be true for other Kuiper Belt objects as well? The question has opened minds to the possibility that the Kuiper Belt might be filled with hidden ocean worlds. Scientists now think that many large dwarf planets in the Kuiper Belt may have started out hotter than we once assumed. When these small worlds formed, the energy from their creation and the decay of radioactive elements inside could have melted their internal ice. In fact, researchers propose that Pluto and similar bodies began with liquid oceans beneath their young crusts. A hot start that meant water was present from the very beginning. Over billions of years, those initial oceans would slowly freeze, but not necessarily completely. In the largest of these far-flung worlds, enough heat might remain trapped inside to keep some of that water liquid, even today. Evidence is mounting that the biggest denizens of the Kuiper Belt still hide reservoirs of liquid water. Observations and models suggest that Eris, a frosty world slightly more massive than Pluto, could have maintained a subsurface ocean since its formation. Makemake, another distant dwarf planet, might also have a buried sea kept alive by internal warmth. Even objects on extremely distant orbits, like Sedna on the fringes of the Sun's domain, are not beyond consideration. Despite its frigid surface, Sedna's interior may hold a remnant pool of liquid kept from freezing by heat from its rocky core and the insulation of thick ice. It appears that even in the Kuiper Belt's deep freeze, nature finds a way to keep water in its liquid state far beneath the surface. The Kuiper Belt, once thought to be a graveyard of frozen worlds, now teases us with the possibility of secret oceans. We can imagine dozens of distant icy bodies, each a tiny world unto itself, harbouring dark, subsurface seas that have persisted for eons. These would be oceans in eternal night, never touched by sunlight, yet potentially stable and enduring. It is a humbling realization that the traditional notion of a habitable zone, the comfortable region around a star, might not tell the whole story. Even at the sun's very edge, far outside the warmth we know, water can remain fluid in the quiet darkness, rewriting the rules of where life might one day be found. Drifting through the Kuiper Belt would be an almost starlit experience. Here, the sun is a distant spark in an ocean of black, and space itself is dark and tranquil. Occasionally, one of these ancient ice worlds might come into view. A remote, cratered sphere, quietly shining in reflected sunlight. It is hard to imagine that beneath its inert-looking surface, there could be motion and warmth. Yet, as we have learned, even these dark, remote corners hold on to the heat of their creation, keeping water in a liquid embrace deep below a shell of ice. It is a lonely realm where the familiar architecture of the solar system fades into a sparse collection of drifting ice and rock. Each of these distant minor planets is like a time capsule, preserving conditions from the solar system's birth. Now we know they might also be preserving liquid water in their cores, defying the cosmic cold. As our journey carries us farther outward, the emptiness grows. But so does the realization that activity and even oceans may persist, where we once assumed only silence and ice. When the New Horizons spacecraft flew by Pluto in 2015, it unveiled a world far more dynamic than anyone expected. One feature in particular captured the imagination: a vast, bright, heart-shaped region on Pluto's surface, gleaming against the darker terrain. This heart, officially named Tombor Regio, holds a smooth, pale plain of frozen nitrogen in its western lobe, called Sputnik Planitia. Unlike the heavily cratered surfaces of many moons, this plain is nearly devoid of impact scars, meaning it is geologically young. In fact, Sputnik Planitia appears to be a gigantic glacier, with patterns on its surface hinting at convection currents slowly churning the nitrogen ice. Such active ice on Pluto's surface immediately raised the question: what is keeping it warm and mobile? The answer may lie beneath Pluto's crust. Scientists suspect that deep under Sputnik Planitia, and perhaps globally beneath Pluto's icy exterior, there is a layer of liquid water. Despite Pluto's frigid surface temperature of about -230 degrees Celsius, an underground ocean could persist if mixed with antifreeze compounds like ammonia or salts. These chemicals would lower the freezing point of water, allowing a slushy sea to remain unfrozen, insulated by the overlying ice. Multiple clues support the idea that Pluto harbours a present-day ocean. The dwarf planet's very shape and gravitational traits hint at a dense layer hidden beneath the surface, perhaps corresponding to a buried ocean. The placement of Sputnik Planitia itself is another clue. This large frozen plain sits almost directly opposite Pluto's companion moon Charon, as though drawn into that position by some subtle balance. Scientists theorize that the extra mass of an ocean beneath the Sputnik Planitia glacier could have caused Pluto to reorient itself, rolling that region toward the moon's steady gravitational pull. Pluto's crust, too, bears evidence of something stirring inside. Vast fractures scar its surface, suggesting that the entire globe has been stretched slightly. Such stretching is exactly what we would expect if an internal ocean gradually froze over time, expanding and pushing the surface outward. Notably, scientists do not see signs of global compression on Pluto, features that would be expected if Pluto had initially been frozen and later melted a bit. This absence of compression and the prevalence of extension hint that Pluto likely began with a liquid ocean that slowly solidified over billions of years, rather than forming its ocean only late in its life. Perhaps most striking is simply the youthfulness of Pluto's surface. Huge water ice mountains tower next to the smooth plains, and there are regions that resemble frozen flows from cryovolcanic eruptions, places where water from the interior may have erupted as slush or ice volcanoes. This level of geological complexity implies an internal source of heat and a reservoir of liquid to drive it. Pluto's core of rock and metal, slowly radiating heat from long-lived radioactive elements, could be enough to maintain a hidden ocean. At the same time, Pluto's thick layers of ice act as a thermal blanket, keeping heat from escaping into space too quickly. Between the internal fire and the insulating shell, Pluto manages to retain a bit of warmth in its depths. The discovery of Pluto's beating heart, a landscape that seems alive with motion, forever changed our understanding of these distant dwarf planets. No longer can we consider Pluto a dormant ice ball at the edge of the solar system. Instead, it appears to be a world with an active interior, one that may still hold a sea beneath its frozen crust. In the soft light of the distant sun, Pluto quietly reshapes its surface with forces drawn from an inner ocean. It is an awe-inspiring thought. Even here, almost 6 billion kilometers from the sun, a tiny planet can keep its heart warm and its waters flowing beneath a shell of ice. On Pluto's surface, midday feels more like dusk. A faint sun hangs low in a charcoal black sky, illuminating a vast expanse of white ice that stretches to the horizon, the western lobe of Pluto's heart. The plains of Sputnik Planitia are so smooth they resemble a frozen sea caught in mid-wave. Jagged mountains of water ice tower at the plain's edge, their peaks catching the feeble sunlight that filters down. The silence here is profound. Only the whisper of a nitrogen breeze might stir the air. In that stillness, one can almost sense the slow churn of ice beneath their feet, the subtle rising and sinking that hint at convection in Pluto's glacier. Sometimes a delicate fog of pale blue haze, part of Pluto's thin atmosphere, hangs near the surface, adding an ethereal beauty. All around is bitter cold, yet far below, a hidden ocean may still be stirring, quietly reshaping Pluto's surface from the inside out. Pluto's moon Charon is a world of its own, half the size of Pluto, and large enough that Pluto and Charon together behave like a double planet. They face each other in a perpetual dance, always showing the same side to one another as they circle their common center of gravity. In 2015, New Horizons revealed Charon's surface in detail, uncovering a stark, greyish sphere marked by surprising chasms and rolling plains. What was once a distant pinpoint of light became a real place, with a history written across its fractured face. One of Charon's most striking features is a vast system of fractures, enormous canyons that rip across its equatorial regions. These chasms are titanic in scale. Some stretch for hundreds of kilometers, and in places they plunge several kilometers deep into Charon's crust. It is as if the moon's surface was once pulled apart, cracking open and creating gaping valleys. Compared to the canyons on Earth or Mars, Charon's fractures are on the same order, or even larger, hinting at a major event in its past that literally tore the moon's outer layers. Scientists believe that this event was the freezing of an internal ocean. Early in Charon's history, heat from its formation, and possibly warming from radioactive elements in its rocky core, could have melted enough ice to form a subsurface ocean of water. For a time, that ocean may have sloshed under Charon's icy crust, locked away in darkness but liquid nonetheless. Eventually, as the small world cooled, the water began to freeze solid. Water expands as it freezes, so the growing ice would have forced the crust outward, cracking it extensively in the process. In essence, Charon nearly split its seams as its internal sea turned to ice, leaving behind the giant canyons we see today. Besides the great chasms, Charon's surface shows other hints of past resurfacing. New Horizons observed smoother plains in certain areas, suggesting that cryovolcanism might have occurred. Perhaps water-ammonia mixtures oozing out and freezing on the surface long ago. But for the most part, Charon is now geologically quiet. Its once liquid interior is likely completely frozen. Still, the moon's cracked visage stands as a record of its youth, when an underground ocean altered the landscape. In Charon's silent canyons and scarps, we see the memory of a sea that has long since gone solid, a frozen testament to a warmer time in this distant moon's past. If an explorer were to stand within one of Charon's great chasms, the view would be otherworldly. Sheer cliffs of ice would rise up on either side, carved by ancient forces. The sky above would be pitch black, dotted with stars, and dominated by the looming presence of Pluto hanging overhead, locked in place as if watching its moon's every move. A faint reddish cap at Charon's northern pole, a stain left by Pluto's gases long ago, adds a blush of colour to the otherwise grey landscape. In the weak sunlight, the fractured ground glows dimly. It is a landscape of frozen stillness now, but one can imagine a time long ago when the ground shifted and cracked as Charon's interior expanded. Back then, these yawning canyons opened up, the crust ripping apart under the pressure of a freezing ocean's final expansion. Today, the moon is silent, but its cracked visage is a testimony to that upheaval, the surface still bearing the scars of a sea that turned to ice. Pluto is not the only dwarf planet at the fringes of our solar system, with secrets beneath its surface. In the distant twilight beyond Neptune, a whole cadre of icy worlds orbits the Sun. Some carry mysterious names: Eris, Makemake, Haumea, Orcus, Sedna, and all of them are part of the same distant family as Pluto. We have not yet seen these places up close, except for Pluto, but what we have learned hints that they too could harbour the remnants of hidden oceans. Take Eris, for example, once touted as the 10th planet when it was discovered, and the object that spurred astronomers to redefine Pluto as a dwarf planet. Eris is nearly the same size as Pluto, and even more massive. It lies even farther out, at times 3 times farther from the Sun than Pluto's orbit. Eris's surface is coated with bright reflective ice. It's so cold out there that what little atmosphere Eris has lies frozen as a delicate frost on the ground. Even in such deep cold, scientists suspect that Eris could conceal a subsurface ocean. Its greater mass means it contains more rock, and thus more radioactive elements in its core to generate heat over time. If Eris formed quickly in the early solar system, it may have started off with a hot interior like Pluto did, allowing an ocean to form under the ice. Billions of years later, that ocean would likely have begun freezing, but perhaps not fully. Though no probe has visited Eris, our theoretical models and the hints we have make it plausible that deep inside this distant world, a layer of liquid water still survives even today. And then there is Makemake, another bright dwarf planet, only a little smaller than Pluto, with a surface covered in frozen methane. Makemake's internal structure remains a mystery, but like Pluto and Eris, it has a mix of rock and ice that could have spawned a subsurface ocean in its youth. Similarly, Haumea, an elongated, rapidly spinning dwarf planet, fascinates scientists with its gleaming water-ice crust. Haumea's violent origin, it was likely struck by another object and set spinning fast, might have bled away much of its internal heat, yet it could have once nurtured a hidden ocean before cooling down. Even beyond these, there are others: Quaoar, Gong, and more, each with its own quirks of size and composition. Together, they raise the question: how many of these distant worlds might have held onto liquid water inside? The Kuiper Belt could be studded with far more ocean-bearing worlds than we ever suspected, each an isolated island of warmth in the outer dark. As our understanding grows, we realize that Pluto was not an odd exception, but perhaps just one member of a vast community of icy worlds with secret seas. Orcus is another far-off world, often called an anti-Pluto, because its orbit is similar to Pluto's, but on the opposite side of the Sun. Orcus is a bit smaller than Pluto, roughly 900 kilometers across, and it has its own moon named Vanth. This moon-to-dwarf planet pairing invites comparisons to Pluto and Charon, raising the question of whether Orcus and Vanth might have experienced tidal heating between them. Early in their history, as Vanth settled into orbit around Orcus, the gravitational tugging could have flexed Orcus's interior and warmed it up. While Orcus is less massive than Pluto, and thus generates less internal heat on its own, the combination of any tidal heating and radioactive decay might have been enough to melt some of its ice. If Orcus ever had a subsurface ocean, it would likely have been smaller and shorter-lived than Pluto's. but it's not out of the question. In fact, if we consider how many of these distant objects have moons, and many do, it opens the possibility that tidal warmth was more common in the Kuiper belt than we realized. Orcus may well have once harbored a hidden ocean for a time, a miniature echo of Pluto's grander sea. As of now, we can only speculate, but Orcus reminds us that even mid-sized worlds on the solar system's edge had their chances to warm up internally. Then there is Sedna, an enigmatic world on an extraordinary orbit that carries it well beyond the main Kuiper belt. Sedna travels on a path that takes it hundreds of billions of kilometers from the Sun at its farthest reach. With a diameter of perhaps around 1,000 kilometers, Sedna is smaller than Pluto, but still large enough to have separated into a rocky core and icy mantle. Its surface has a reddish hue from organic compounds, and it spends most of its immense journey in a realm of almost perpetual night, where the Sun is just a distant star. Could Sedna have kept enough internal warmth to sustain a pocket of liquid water? Some calculations suggest that if Sedna's core contains a substantial amount of radioactive elements, it could indeed retain a subsurface ocean for a long time. This would be especially true if the water was mixed with ammonia or other antifreeze chemicals, keeping it liquid at lower temperatures. Sedna's extreme distance also means that any heat it has is lost very slowly. With so little solar energy reaching it and a vacuum around it, there is not much to carry heat away. No spacecraft has visited Sedna, so for now these ideas remain hypotheses. Yet Sedna stands as a tantalizing possibility. Despite being one of the coldest, most remote objects known, it might still guard a hidden ocean in its depths. It is remarkable that many of these distant dwarf planets might be more than just frozen rock and ice. In each of these far-flung worlds, Eris, Orcus, Sedna, and their kin, there lies the possibility of internal warmth and perhaps a secret sea, though the sun's light barely reaches them and their surfaces are numbingly cold. Their interiors could still harbour liquid water that has persisted since the time they formed. It may be many years before a spacecraft visits these remote worlds, but already our theories and a few tantalizing clues allow us to imagine oceans concealed beneath their ice in perpetual darkness. These distant siblings of Pluto broaden our understanding of where water can remain fluid, extending the known boundary of ocean worlds to the very edges of our solar system. Visualize standing on Eris, at the far fringe of the Sun's influence. The Sun is an almost star-like point, barely lighting the frozen landscape around you. The ground is coated in methane and nitrogen frost, gleaming faintly under a pitch-black sky. The silence is absolute, and the cold is beyond any earthly winter. Yet deep beneath your feet, miles below the surface, there might be a reservoir of liquid water, heated by Eris's own internal warmth. That idea brings a whisper of comfort to an environment otherwise ruled by unimaginable cold. High above, the stars crowd the sky, and among them a tiny moving point. Perhaps Eris's little moon Dysnomia circles quietly, a distant companion in the void. Out at this distance, time itself seems to slow, and the sun's warmth is little more than a memory. But deep inside Eris, time might be marked by the slow, steady currents of a buried ocean. Even here, at the very edge of the solar system, a hidden sea could quietly endure in defiance of the freezing darkness. How can liquid water persist in places so far from the sun's warming rays? This question has quietly transformed our understanding of the outer solar system. At first glance, worlds like Triton, Pluto, or distant Eris seem far too cold for any kind of activity. Their surfaces are frozen hard, and sunlight provides almost no warmth. Yet we now know these distant realms can harbour internal oceans and even active geology. The secret lies in sources of heat and insulation that do not depend on the sun at all. One key to keeping water liquid in the deep cold is internal heat. Large moons and dwarf planets often have a substantial amount of rock mixed with their ice. That rock can generate heat through the slow decay of radioactive elements, providing a steady warmth from the core outward. Even a small trickle of heat, if trapped beneath a thick layer of insulating ice, can prevent all the water from freezing solid. Over millions of years, this internal furnace can maintain a subsurface ocean, quietly warming it from below, while the vacuum of space keeps the heat from escaping too quickly. This means that even a far-flung icy moon, bereft of sunlight, can keep part of its interior warm and wet, purely due to the slow, steady heat released by its rocks. Another natural furnace for these worlds is tidal heating. When a moon orbits a giant planet in a slightly oval, elliptical path, the changing gravitational pull flexes the moon's interior. This flexing is like kneading a ball of clay. Friction generates heat inside. Closer to the Sun, Jupiter's moon Io is constantly flexed and kept molten by this effect, and Europa's ocean stays liquid thanks in part to Jupiter's tugs. In the colder reaches, we see hints of tidal heating as well. Triton likely warmed up when Neptune captured it. Miranda's strange geology also speaks of past tidal tug-of-wars. Even smaller dwarf planets with moons, like Pluto with Charon or Orcus with Vanth, might have experienced a burst of tidal warmth early on, enough to melt ice into water. In essence, gravity itself becomes a source of heat, kneading and squeezing a moon until its insides stay warm. Chemistry also lends a helping hand. The water in these hidden oceans is not pure. It's often laced with other substances such as ammonia, salts, or methanol. These act as natural antifreeze, lowering the freezing point of water significantly. Ammonia, for instance, can keep water liquid at temperatures tens of degrees below 0 degrees Celsius. So even as the world's internal temperature drops, the water can remain a cold, briny liquid rather than turning to solid ice. This antifreeze effect extends the life of any subsurface sea, allowing it to persist for billions of years in environments where pure water alone would have frozen solid long ago. A thick, icy crust can act like a thermal blanket, locking heat inside a moon or planet. The outer surface might be incredibly cold, but just a few dozen kilometers down, the temperature can rise substantially. Ice is a poor conductor of heat, especially at the ultra-low temperatures of these distant worlds, so internal warmth leaks out only at a glacial pace. That means any heat generated inside, whether from flexing tides or radioactive minerals, has a chance to accumulate and keep an ocean warm beneath the frigid shell. On Earth, we see a similar principle in action beneath Antarctica's ice caps, where liquid lakes endure under kilometers of ice, untouched by the sun yet unfrozen thanks to Earth's inner heat and the insulation above. Through these mechanisms, tidal friction, radioactive decay, chemical antifreeze, and insulating ice, even the most distant ocean worlds can remain active internally. They challenge our preconceived notions of what a livable environment might be. In places where the sun's influence is but a feeble glimmer, there can still be energy and warmth enough to sustain liquid water. It is a testament to nature's resilience that the recipe for an ocean does not require direct sunlight at all. As we continue our journey, we begin to see that the potential for life's essential ingredient, liquid water, extends far beyond the traditional habitable zone, hiding in the coldest corners of our solar system. Deep inside every rocky body in the solar system, an ancient fire still burns. It is not a fire of flames, but a slow release of heat from radioactive elements embedded in the rock. When planets and moons formed, they incorporated atoms of uranium thorium, potassium, and others that naturally decay over time. Each decay event releases a tiny bit of energy as heat. Over millions and billions of years, these countless atomic decays act like a low-wattage heater that never completely turns off. This radiogenic warmth is a critical reason why subsurface oceans can survive on distant worlds. Even in the absence of sunlight or strong tidal forces, the interior of a moon or dwarf planet may stay warm thanks to the steady trickle of heat from its rocky core. The larger the object, and the more rock it contains, the greater the potential heat output. For example, Pluto, with its substantial rocky core, generates more internal heat than a smaller ice-rich comet would. In the cases of Uranus's moons, like Titania and Oberon, calculations show that heat from radioactive decay alone could be sufficient to maintain a layer of liquid water deep inside, provided the heat is well insulated. One remarkable aspect of radioactive heat is its persistence. The elements that produce this heat have extraordinarily long lifetimes. Uranium and thorium isotopes take billions of years to decay. That means worlds that formed alongside the Sun 4.5 billion years ago still have a significant portion of their original heat slowly emanating from their interiors, even now. In the early days of a moon's history, radiogenic heating would have been stronger, augmented by shorter-lived isotopes that have since faded away, possibly helping to melt internal ice and start an ocean. Today, though diminished, the remaining warmth is often just enough to keep those ancient oceans from freezing solid. We see evidence of this internal heating in places like Ceres, the dwarf planet of the asteroid belt, which shows signs of past, and perhaps present, subsurface brine pockets, likely sustained by internal heat. Even Saturn's small moon Mimas, long thought too frozen to have anything liquid, has hinted at an internal ocean in recent observations. Some scientists speculate that a combination of slight tidal flexing and heat from radioactive decay in its core could explain how Mimas might be warm enough inside for liquid water. These examples show that radiogenic warmth is at work even in unexpected small worlds, quietly enabling liquid water where we once assumed none could exist. It is in the far distant worlds, like Pluto and Eris, however, that radiogenic heat truly becomes the hero of the story. Far from any strong tidal influences, these isolated spheres rely almost entirely on the warmth from within to keep their buried seas alive. It is humbling to realize that the faint heat of ancient radioactive atoms, quietly decaying in darkness, can make the difference between a dead sphere of ice and a world with a secret ocean deep inside. Even without sunlight, the geology and chemistry of these worlds provide a lifeline of warmth that allows liquid water to persist against all odds. Without this internal heating, the outer solar system would likely be a far more static place. Radiogenic energy provides a baseline temperature, a gentle heat that ensures not every corner of these remote worlds turns to solid ice. It underpins the longevity of subsurface oceans, acting as a slow-burning candle deep below the surface. This heat from within, combined with the insulating effects of ice and occasional boosts from tidal or other sources, is what allows water to remain liquid against the odds. In a sense, the internal radioactive fires are the heartbeat of these cold, distant worlds, faint and steady, but vital to sustaining their hidden seas. We have now traced the possibility of liquid water to the very edge of our Sun's domain, from the inner moons of Jupiter, out to dwarf planets like Pluto, and even further to Sedna. The prospect of hidden oceans extends across an astonishing range of environments. Even in the dimmest outskirts, where the Sun is little more than a distant point of light, the ingredients for an ocean world can come together. These are the most distant seas that still orbit our sun, reservoirs of water kept liquid in places once deemed too cold and too remote for anything but solid ice. It is awe-inspiring to consider that somewhere out beyond Pluto, perhaps in the Oort cloud where comets dwell, there could be other unseen worlds preserving internal seas. As long as an object has enough mass and the right mix of rock and ice, it may carry its own warmth and water even at the extreme fringes of the solar system. The concept of a habitable zone, traditionally the band around a star where liquid water can exist on a planet's surface, suddenly seems too narrow. We've learned that a habitable zone can also exist deep inside icy moons and planets, powered by internal heat rather than sunshine. In effect, the sun's reach in nurturing oceans is far broader than we ever imagined, because its planets and moons have their own inner fire. Standing here at the edge of our solar system, we can't help but wonder what lies beyond. Our sun is just one star among billions. If hidden oceans are possible here in the freezing darkness, how many might exist circling other stars? Might there be exoplanets or exomoons with subsurface oceans waiting under alien skies? The discoveries in our own cosmic backyard give us hope that seas under distant suns might be common, perhaps refuges for life in the universe's cold, dark places. As we prepare to venture beyond our sun's influence, the stage is set to seek out these alien ocean worlds that orbit other stars, carrying forward our quest to find water in the cosmos. We drift away from the familiar shores of our solar system and into the cosmic ocean of stars beyond. Out here, the night sky brims with distant suns, each one a beacon that could warm its own family of planets. Not long ago, these other worlds were only a dream, points of light in telescopes, their presence suspected but unconfirmed. Today, thousands of exoplanets have been discovered, revealing an astonishing diversity of worlds circling distant stars. The universe has unveiled itself, not as empty space between stars, but as a vast sea filled with planets of every kind, expanding the horizons of our search for alien oceans and life. Each new world we find carries a whisper of possibility. Astronomers detect subtle wobbles in starlight or tiny dips in a star's brightness as a planet passes in front. From these faint signals, entire worlds emerge in our imagination. We learn their sizes, their orbits, and sometimes a hint of their atmospheres. Some are scorched giants, skimming close to their stars. Others are frozen, distant wanderers. But among them, the most tantalizing are those that might be temperate, not too hot, not too cold, places where liquid water might pool or flow. In those gentle environments, we imagine oceans spreading across a planet's surface, gleaming under an alien sun. Water is a key that unlocks our hopes of finding life beyond Earth. On our own planet, water was the cradle that nurtured the first living things. It remains the lifeblood of every creature, every ecosystem, connecting all forms of life in a grand aquatic lineage. Knowing this, we gaze up at the stars and wonder, how many of those distant worlds hold water in their landscapes? Could there be seas and lakes on a world hundreds of light years away, quietly harbouring life of their own? This promise of exoplanets, the chance that some are living, ocean-bearing siblings to Earth, stirs a deep curiosity and a sense of cosmic kinship. Already, there are clues that water is abundant in the cosmos. The basic elements of water, hydrogen and oxygen, are among the most common in the universe. In distant nebulae, we see the spectral fingerprints of water vapour. In our own solar system's outskirts, comets carry frozen water as a reminder that space beyond Earth is not dry. Even among the exoplanets we have studied from afar, astronomers have detected water's signature in the atmospheres of some giant planets. These findings are like messages in a bottle from across the galaxy, each telling us that the ingredients for oceans are spread widely, awaiting the right conditions to gather into liquid seas. The sheer number of exoplanets discovered gives reason for optimism. With each new planet catalogued, the odds improve that one of them might resemble our own watery home. Some orbit stars similar to our Sun, at distances where sunlight would be gentle enough for water to remain liquid. Others circle faint red dwarf stars, and despite the differences in those environments, we wonder if they too could host a stable ocean. Every world is unique, but the laws of nature repeat throughout the cosmos. Planets form from disks of gas and dust that surround newborn stars, and water ice is a common ingredient in those disks. It seems inevitable that many planets, near or far, carry water, whether locked in ice, adrift as vapor, or flowing as liquid on or below their surfaces. From time to time, scientists announce the discovery of a particularly intriguing planet, one that sparks headlines as a possible new Earth. The imagination leaps at these reports. We picture a distant globe covered in blue, clouds swirled in its sky, continents, or perhaps endless ocean beneath. We picture the glow of its sun reflecting off water, a blue marble shining from across the light years. While reality may be more complicated, these imaginings drive us onward. The promise of exoplanets lies in their potential to surprise us. Among them might be worlds with landscapes and seascapes as breathtaking as any seen on Earth, or even more so, shaped by exotic atmospheres and suns of different colours. For humanity, the realization that planets are common has been a profound shift, like opening a door onto a much larger universe. In centuries past, we could only speculate about other worlds. Now, with sensitive instruments and clever techniques, we can map the orbits of planets around distant stars and estimate their climates. Yet for all we can infer, these places remain tantalizing mysteries. We cannot yet visit them or see their oceans directly. But in our minds and through our science, we journey there. We sail the light of distant suns, imagining the feel of a cool alien sea breeze or the sight of twin moons hanging over a distant ocean horizon. Each exoplanet discovered is a story that has only just begun. We give them catalogue designations, or sometimes names. But what are they truly like? We wonder how the sun feels on those foreign skies, and if rain falls on their soil or seas. The promise held by these distant worlds is that one day, perhaps, we might find a place that echoes Earth, or even encounter something utterly unanticipated, a new chapter in the story of worlds. It's a reminder that the cosmos is not a sterile void. It is fertile with planets, many of which could be water-rich. As we continue to search, each clue and each discovery draws us deeper into the cosmic ocean, urging us onward in the quest to find our cosmic neighbours who share a bond with us through water and life. In this vast search, we stand on the shoreline of the cosmic ocean, peering out. Our tools, telescopes, probes, and spectroscopes, are like ships carrying our senses across the void. With them, we have begun to chart the archipelagos of planets scattered around other stars. We have glimpsed only the nearest few, but already the diversity astounds us. Among the gas giants and rocky terrestrials, scorched and frozen worlds, there are those that seem to beckon with temperate conditions. This journey into the unknown carries the promise of finding oceans beyond our own, broadening the definition of home. As we wade deeper into these stellar seas, we realize that the story of water in the universe is only just unfolding, with countless chapters still to be discovered on worlds yet unseen. When scientists speak of finding another Earth, they often start by looking for the habitable zone around a star. This is the distance from a star where conditions could be just right for liquid water to exist on a planet's surface. They call it the Goldilocks zone, invoking the fairy tale idea of something being neither too hot nor too cold, but just right. For a planet, being in this comfortable belt means it isn't baked dry by stellar fire, nor frozen in eternal ice. It is here, in this temperate ring of space, that we imagine oceans could persist for eons, nourishing life under alien skies. Every star has its own habitable zone, the boundaries set by its brightness and heat. Around a small, cool star, the zone hugs in close, perhaps so near that a year there lasts only a few weeks or days. Around a larger, hotter star, the zone lies farther out, at distances where planets may take many Earth years to complete an orbit. Our Sun's habitable zone is the space where Earth orbits, a fortunate middle ground, allowing our oceans to endure for billions of years. Closer to the Sun, Venus likely lost any ancient waters to a runaway greenhouse effect. Farther out, Mars sits at the chilly edge of the zone, where liquid water appears only briefly or remains locked underground. These examples teach us how critical a star's gentle warmth is for keeping seas alive on a world's surface. The habitable zone is a guiding light in the quest for life, but it is not a guarantee. A planet's own character matters greatly. If it lacks an atmosphere or has too thin a one, even a perfect orbit might not prevent its water from evaporating into space or freezing solid. If its atmosphere is too thick with greenhouse gases, it might swelter despite being at a safe distance, turning any seas into steamy cauldrons. So while the habitable zone idea narrows our search to promising regions, we know that being in the right place is only one part of the story. Still, it is a vital piece, like finding the shoreline when you're searching for islands in a vast ocean. The habitable zone points us to where planetary oceans might lap at the cosmic beach. With this concept in mind, astronomers have scanned the skies for planets that receive just the right amount of starlight. The Kepler Space Telescope, for example, spent years staring at one patch of sky, watching for the faint flicker of planets passing in front of their stars. Among its trove of discoveries came the first small worlds found to lie within their stars' habitable zones. When those findings emerged, they caused a ripple of excitement. At last, evidence that somewhere out there, conditions might vaguely resemble those of home. Names like Kepler 22b and Kepler 186f entered the conversation. Distant planets orbiting in temperate twilight, possibly neither hellishly hot nor bitterly cold. One by one, the list of such worlds has grown. We now know of a handful of rocky or near-rocky exoplanets situated in that life-friendly band around their stars. These planets are of particular interest because they hold the potential for surface oceans. We picture them as places where rain might fall and rivers flow into alien seas. Perhaps some are water-rich, with chains of islands or expansive archipelagos dotting their surfaces, or even completely ocean-covered, with not a speck of land to break the waves. Although we cannot yet confirm the presence of water on these worlds directly, their orbits suggest that if they have water, it could remain liquid, rather than being locked away entirely as ice or vapor. Thinking of the habitable zone also reminds us of how special our Earth's position is. A little closer to the Sun, and our planet might have become a second Venus, scorched and desiccated. A bit farther, and it could have ended up like Mars, cold and dry. The Earth's orbit, just so, allows sunlight to bathe our world in a gentle, life-sustaining glow. In that light, our oceans have thrived. So as we seek planets in other habitable zones, we are essentially looking for worlds that have won a similar cosmic lottery. These would be planets that, like Earth, bask in just the right amount of warmth for seas to glisten on their surfaces over geological timescales. Yet, the concept of habitability is evolving as we learn more. We realize that even outside the classical Goldilocks zone, life could find niches. We've seen it around deep-sea vents on Earth and in subsurface lakes on icy moons. But for abundant, surface-dwelling life and sprawling oceans under open skies, being in the habitable zone remains a crucial factor. It sets the stage for a world that might look something like our own, with perhaps blue skies and clouds drifting over open waters. It is in these zones that we focus many of our searches, because here we have the best chance to find a truly Earth-like planet, a place where one day we might imagine waves crashing on a beach or an alien sunset mirrored in a calm sea. The idea of the habitable zone is both humbling and hopeful. It highlights the fine balance required for life as we know it, a balance struck perfectly on Earth, and we hope, on some distant shores as well. As we map out these zones around other stars, each one becomes an invitation to wonder. We know the distances and the starlight that bathe these planets, but not the details of the worlds themselves. Are they lush or barren, ocean-covered or desert-dry? Those answers remain hidden, yet the very fact that these zones and their planets exist stirs our imagination. It reminds us that Earth's life-friendly conditions may not be unique. Nature could recreate similar oases on other worlds. The habitable zone, ultimately, is a way of finding the places where the cosmos might have brewed up its own versions of seas, perhaps even teeming with life gazing back under a sun of their own. As our tools improve, this habitable zone idea is beginning to be tested against real observations. With new space telescopes peering into exoplanet atmospheres, scientists have glimpsed indications of water vapor high above some distant worlds. On a few occasions, the spectral imprint of water has been seen filtering through the clouds of a far-off planet, suggesting that if we could descend through those alien skies, we might find misty vistas and perhaps oceans below. These early hints invigorate the search. They tell us that the habitable zone is more than an abstraction. It is a realm we can explore from afar. Each bit of evidence, be it a moist atmosphere or a stable climate, brings us closer to confirming that another blue world might indeed circle a distant sun. Among these, red dwarf stars, those small and dim embers of the galaxy, offer a very different backdrop for any ocean-bearing world. They are the most common stars, far more numerous than stars like our Sun, and their planets are among the first where we've sought signs of habitability. Around these cool reddish stars, the habitable zone nestles much closer in. A planet could orbit its red dwarf sun in a matter of days or weeks and still receive the gentle warmth needed for liquid water. This means an Earth-sized planet can cling close to a tiny star and possibly cradle an ocean while locked in an eternal embrace with its sun. Life near a red dwarf would experience a perpetual intimacy with its star. Because the habitable zone is so close, these worlds often tidally lock. One hemisphere faces the star in unending daylight, while the opposite side lies in permanent night. It's utterly unlike Earth's own day-night cycle. Yet in that alien arrangement, a delicate balance may allow water to endure. On the sunlit side, an ocean could spread under a dusky red sky, never cooling enough to freeze. On the dark side, far from the star's gaze, water might freeze into a cap of ice. Between these realms of light and dark, along the line of perpetual dawn and dusk, could lie a ring of twilight where temperatures are just right. In that band of eternal evening, an alien ocean might lap at rocky shores. These theoretical worlds are sometimes whimsically nicknamed eyeball Earths. Seen from afar, the day side might appear as a blue pupil of ocean encircled by a white iris of ice on the night side. For a world with enough water and air, the day side might not scorch and the night side might not freeze solid. Winds and currents could carry heat around, softening the extremes. In the endless afternoon of the day side, under a dim but coppery sun, an ocean could stay liquid and lively. On the night side, perhaps only the tops of oceans freeze, or maybe interior warmth keeps the darkness from being completely frozen. The terminator, the boundary between day and night, might be the most comfortable zone of all, bathed in a permanent sunset glow with a mild climate. One might stand there and see the star forever hanging on the horizon, while waves gently reflect its ruddy light. To imagine an ocean on such a tidally locked world is to imagine something both familiar and alien. The water itself would still ripple and flow in familiar ways. Waves would break and tides would rise and fall, perhaps influenced by the pull of nearby moons or other planets. But the colour of the daylight would be unlike any noon on Earth. A red dwarf star emits a deeper, redder light. An afternoon might feel like an earthly sunset, stretched out indefinitely. If there are clouds, they might glow pink or orange against a dim burgundy sky. The ocean, if rich in algae or life, might even take on unusual hues under the spectral glow of a red sun. On the endless night side, illumination would come only from stars, and perhaps a faint aurora shimmering if the planet's magnetic field dances with the stellar wind. Such an ocean under the starry dark would be eerily beautiful, a mirror reflecting constellations never seen from Earth. Real worlds akin to these visions have already been found. One of the most celebrated discoveries is the TRAPPIST-1 system, a family of 7 Earth-sized planets orbiting a small, feeble red dwarf star about 40 light-years away. Several of those worlds lie within or near the habitable zone of their tiny sun. If we could travel there, we might find a sky where that dim star looms relatively large, glowing a gentle red. On some of the TRAPPIST-1 planets, the gravity of neighbouring siblings draws them into rhythmic dances, and those other planets might appear as sizable moons in each other's skies. It's tantalizing to wonder if any have oceans. Scientists suspect that some of these planets could be rich in water, perhaps as global oceans or thick ice shells, based on their densities and models of their formation. As we speak, telescopes are scrutinizing the TRAPPIST-1 worlds, searching their atmospheres for traces of water vapor or protective gases that might shield oceans and life below. Even closer to us, the nearest star beyond our Sun holds its own intriguing planet. Proxima Centauri, a red dwarf just 4 light-years away, has a world in its habitable zone. Proxima b. This planet is roughly the mass of Earth and orbits its dim sun every 11 days. Bathed in the dim red glow of the closest star in the sky, Proxima b could potentially have temperatures suitable for liquid water if it carries an atmosphere to distribute the heat. We don't yet know if oceans actually grace its surface, but the mere possibility makes the night sky feel a bit less lonely. When we look toward the constellation of Centaurus and know that a planet circles the very nearest star with a chance of seas and perhaps life, the vast gulf between stars suddenly seems a little smaller. Red dwarfs pose challenges for life. Young red dwarfs can be tempestuous, unleashing flares and intense radiation that could strip a planet's atmosphere or sterilize its surface. A world around such a star might need a strong magnetic field or a thick atmosphere, or perhaps a deep ocean to protect any fragile beginnings of life. On the other hand, red dwarfs burn so slowly that they shine for trillions of years, far longer than stars like our Sun. This gives any surviving life a very long window to evolve and thrive. Once the star's youthful fires calm down, one can imagine ancient oceans under a quiet, stable red dwarf 1 trillion years from now, long after our Sun has expired, still gently stirring with tides, and perhaps life that has all the time in the universe to develop. So, in the cosmic dance of habitability, red dwarfs offer a paradox. Worlds orbiting them may face harsh beginnings, yet have the potential for long, enduring lives. If some of these dim stars host blue oceans, then despite the differences in light and climate, water could play the same life-giving role it does here. It is a comforting thought that even around the most common stars, nature might find a way to keep seas of liquid water. Under ruby skies, on worlds locked in strange synchrony with their suns, the song of the ocean might still whisper along alien shores. In those whispers, if we could ever hear them, might lie stories of life that has adapted to days that never end and nights that never lift. Life that knows a different kind of sun, but still finds a home in water. Beyond the Earth-sized realms lie planets that are larger and more massive, and these too spark our imagination about oceans. So-called super-Earths, worlds a few times heavier than our planet, and mini-Neptunes, smaller than the ice giants of our solar system, represent common types of exoplanets that we don't have here at home. They occupy a middle ground in size and composition, and scientists suspect many could be water-rich. On some of these worlds, vast oceans might cover the surface to great depth, unfettered by continents. Others might have thick atmospheres shrouding deep, hot seas beneath permanent clouds. These are planets where an ocean could be not just a feature, but the defining characteristic of the entire world. Super-Earths are rocky planets larger than Earth. With more mass, their gravity is stronger, and their landscapes might be quite unlike ours. If a super-Earth has abundant water, that water could form a global ocean, tens of kilometers deep or more. Under a heavier gravity, water would press down with tremendous force. The ocean floor, if one exists, would experience pressures far beyond those in Earth's deepest oceans. In those crushing depths, water may transform into exotic ice, not frozen by cold, but pressed solid by extreme force. Layers of high-pressure ice could line the deep interior like bedrock, while above them, the ocean remains liquid. It's strange to imagine an ocean floor made not of rock, but of ice. Yet this may be common on such enormous water worlds. The surface conditions on a super-Earth ocean planet could also be unique. The higher gravity holds onto a thicker atmosphere, likely forming a dense blanket of cloud and mist. Daylight filtering through such an atmosphere might have a diffuse, soft quality, with warm hues of red or orange if the air is very thick. Winds in that heavy air might blow with different force, and the crash of waves could sound deeper under stronger gravity. By the shore of such an ocean, a human would feel the weight of air and water more intensely. Waves might break shorter and quicker under the strong gravity. Everything would seem subtly altered in scale, yet the sight of a vast ocean reaching the horizon and reflecting the light of a foreign sun would still inspire a familiar sense of wonder. Then there are the mini-Neptunes, slightly larger than super-Earths, which may have no solid surface at all. These planets likely have thick envelopes of gas around them. but many are thought to conceal deep layers of water or slushy ice beneath their atmospheres. Imagine descending into the sky of such a planet. As you fall through thick, cloud-laden air, the pressure and temperature rise. Eventually, you would encounter a vast ocean where the atmosphere blends into warm seas in a continuous gradient. There may be no clear line between sky and sea, only a gradual thickening of cloud into water. In such warm, Neptune-like worlds, water could be extremely hot, even supercritical, neither truly liquid nor gas, creating an environment utterly unlike any ocean on Earth. The diversity of these exoplanets is astounding. Some super-Earths might actually be mostly rock and metal, dry and solid from crust to core. Others, however, could be swathed in water, thousands of kilometers deep. Mini Neptunes might look tranquil from space, with a pale blue-white hue of haze, but beneath their clouds, they could hide global seas under crushing atmospheres. Each new discovery adds a piece to the puzzle. One of the first candidates for a water-rich world was an exoplanet called Gliese 1214b. It is a super-Earth orbiting a dim red star about 48 light-years away. Its measured density suggests it is neither pure rock nor light gas, but something in between, possibly a planet with a substantial portion of water. When astronomers looked at Gliese 1214b's atmosphere, they found it was likely veiled by a thick, concealing haze. Many suspect that beneath those clouds lies a steamy global ocean. Although Gliese 1214b is too hot for life as we know it, its dayside temperature is scorching. The fact that it exists was an exciting proof of concept that such exotic aquatic worlds are out there. Another intriguing world is K2-18b, a super-Earth about 8 times the mass of Earth, orbiting in the habitable zone of its star. In 2019, scientists announced the detection of water vapor in K2-18b's atmosphere, the first time water was found on a potentially temperate exoplanet. It was a groundbreaking discovery, revealing a signature of water on a world outside our solar system that could potentially have mild temperatures. The find sent ripples of excitement through the scientific community. K2-18b is likely not a rocky Earth twin. It's larger and may have a thick hydrogen atmosphere, but beneath that gassy envelope could lie a liquid ocean. If so, it would be a global ocean under a sky very different from ours. Perhaps a deep, pressurized water layer hidden below clouds. The presence of water vapor tells us that K2-18b has the ingredients for a water environment, and it blurs the line between what we consider habitable and what might actually support life. What would it be like to visit such a planet? If we could send a probe into a mini Neptune's atmosphere, it might descend through layers of thick clouds, buffeted by strong winds, until finally plunging into a vast ocean. It would find an environment utterly dark at depth, warmed perhaps by the planet's core, and blanketed above by an endless stormy sky. On a super-Earth water world with clearer skies, a floating explorer might record endless horizons and constant rolling waves under a foreign sun, an ocean that truly has no end. These visions remain speculative, but they are grounded in what our science suggests about these distant places. In dreaming of super-Earths and mini Neptunes with oceans, we extend our idea of what a shore can mean. It may not be a beach on solid ground. Instead, it could be the boundary between water and sky, on a world with only ocean below and clouds above. Yet even there, in that alien simplicity, the essence of a sea remains the same. Water moving in waves, light dancing on its surface, and perhaps life teeming within. These planets remind us that an ocean need not mirror Earth's to be a thriving world. Rock and water can mix in different proportions to create entirely new kinds of ocean planets, some calm and milky under permanent cloud, others storm-tossed and blue beneath a dim sun. They underscore the versatility of water as an agent of geology and life. Wherever enough water gathers, even light years away, it finds a way to carve out seas and perhaps cradle living things. What if a planet had no land at all? Nothing but ocean from pole to pole. Such a world would be a true water planet, an ocean without end. Astronomers call these hypotheticals water worlds or aquaplanets, and they could be common among the exoplanets. On a water world, there are no continents to break the waves, no mountains or deserts, just a global sea encircling the planet. From orbit, it would gleam uniformly blue, or perhaps green with life, with white cloud streaks, a marble of water and sky. Standing on such a planet's surface, perhaps on a boat or floating platform, since there is no solid ground, you would see ocean stretching to every horizon. Every direction is seascape, and the sun would both rise and set over water each and every day. Earth itself is tantalizingly close to being a water world. Over 70% of our surface is ocean. And in fact, scientists suspect that in its distant past, Earth might have had much less land visible, possibly resembling a water world for millions of years. Plate tectonics and the emergence of continents eventually broke the ocean's total dominance here. But elsewhere, that might not happen. If a planet is slightly wetter than Earth, or a bit flatter in its geology, it could easily end up entirely ocean-covered. Just a few more deep trenches, a few fewer highlands, and even our planet would have been all sea. This realization makes water worlds feel not so alien after all. They are an extreme on a continuum that includes Earth. On a planet with no land, the interplay of ocean and atmosphere would set the stage for everything. Waves could grow truly gigantic without continents to halt their fetch. One can imagine rolling swells that travel around the entire globe unimpeded, merging and growing over vast distances. The weather might have patterns unlike any on Earth, since the entire surface contributes moisture to the air. Perhaps there would be perpetual bands of rainfall and storms circling the planet. Without land masses to break up circulating currents, ocean streams might form endless loops. A current of warm water could theoretically circumnavigate the world, creating a band of tropical warmth. Likewise, a cold current could ring the planet at higher latitudes. The climate in such a world might be surprisingly uniform, with water distributing the sun's heat efficiently, or it might break into distinct belts of different weather. Either way, every raindrop would fall into the sea, and every wind would blow over waves. Life on a completely oceanic planet could flourish in the sea. Our own oceans are teeming with life, even far from shore, from microscopic plankton to great whales, all without needing land. In an endless ocean, life might develop incredible diversity in the open waters and the depths. Perhaps forests of floating algae mats would drift on the surface, forming ever-shifting pseudo-continents of organic matter that come together and break apart with the currents. Maybe entire ecosystems would exist around nutrient-rich upwellings or around thermal vents on the seafloor, just as they do in Earth's deep oceans. Intelligent life, if it emerged, would have only water to work with. Its challenges and inventions would revolve around currents, buoyancy, and maybe tools made from shells or metals deposited at hydrothermal vents. Without fire or metal smelting, an aquatic civilization would be very different from our own. But one can still imagine sentient beings navigating by the stars reflected on their endless sea, telling stories about the fathomless world beneath. Their entire existence would be bound to the water. From a day-to-day perspective, a water world could be at once monotonous and beautiful. Monotonous because the scenery might not change dramatically. There is no new valley or plateau beyond the horizon, only more water. But beautiful in that this world presents an unbroken, pure interface between ocean and sky. Imagine a crimson sunset that spans the entire 360-degree horizon, or a night where the full moon paints a silver pathway across the water, uninterrupted by any land. The colours of the sky would constantly play on the sea's surface. Cloud formations would be reflected in mirror-smooth calm areas, or shattered into glitter by windy chop. Storms would march over the water with curtains of rain and spears of lightning, and nothing would hold them back. For any creature living there, the sea would be everything: provider of food, absorber of sunlight, cradle of life, and an endless mystery below. Astronomers are actively searching for signs of such water worlds. If a distant planet with the right size and temperature also shows evidence of a lot of water vapor in its atmosphere, it raises the possibility that oceans cover it completely. One recently discovered exoplanet is suspected to be just that: an Earth-sized world engulfed by a deep global ocean. We can't yet map its surface to confirm the absence of land, but its density and other clues hint at an all-water composition. Future telescopes may be able to observe such a planet in more detail, for example, by detecting the glint of starlight off a vast liquid surface, or by noticing a lack of the seasonal signals that continents and forests produce. For now, these worlds remain theoretical, but strongly hinted at by the data. If we ever confirm a true ocean planet, it will be a profound milestone. A planet even more oceanic than Earth. We might nickname it after ancient sea gods and daydream about what its marine life could be like. Knowing it exists would also prompt deeper questions. How does a water world form? Did it have less geological activity to raise land, or simply so much water that land never stood a chance? And of course, there's the question of life. Could an all-ocean planet develop living organisms, and perhaps even complex life? Many scientists think yes, pointing out that life on Earth began in the oceans and did quite well there for billions of years before ever venturing onto land. In contemplating water worlds without continents, we recognize how versatile nature's habitats can be. Life on such a planet would know water as its sky and its soil, entirely self-contained in a blue realm. Absence of land doesn't mean absence of drama or complexity. Currents and climates, ecologies and evolution would all still play out on a vast liquid stage. To us, looking from afar, such a world would be a compelling vision of both strangeness and familiarity. Alien in its lack of solid ground, yet familiar in its embrace of water, the element that binds all known life. It reinforces a comforting idea. The same blue that signifies life on Earth could also glisten on the surface of another world, signalling oceans without end under foreign skies. Not all oceans in the cosmos are made of water. Under alien skies, there might be seas of liquid chemicals that are unfamiliar, lakes of methane, ethane, or even oceans mixed with ammonia. Our own solar system gives us a hint. Saturn's moon Titan is shrouded in an orange haze and dotted with lakes of liquid methane and ethane. On Titan, it literally rains hydrocarbons, and rivers of methane carve channels in the icy ground, flowing into dark, oily lakes. This shows that in the right conditions, other liquids can take on the role that water plays on Earth. Imagine an entire world covered not in blue water, but in seas of a different hue, perhaps a black, mirror-like methane ocean, reflecting a dim, copper-coloured sky, or an ammonia-rich sea shimmering under the pale light of a distant sun. A planet with seas of liquid methane would be an eerie sight. Methane is a lighter fluid than water and exists in a far colder realm. Picture standing on the frozen shore of such a sea, bundled in an insulated suit, as the temperature would be tens of degrees below zero. The liquid before you would be as clear as gasoline and maybe tinged with amber or brown from complex organic molecules. The sky might be filled with a perpetual smog, as sunlight, likely feeble if the planet is far from its star, triggers chemical reactions in the atmosphere. When it rains, it would rain drops of liquid methane, a cold, slow drizzle that forms puddles and feeds the alien ocean. Waves on a methane sea would lap gently. In Titan's low gravity, they are sluggish and small. But on a larger world, with stronger gravity, methane waves could crash on alien beaches with a unique sound, perhaps softer or higher pitched than waves of water, because of methane's different properties. Ammonia, too, can act as a liquid solvent on frigid worlds. In fact, a mixture of water and ammonia has a lower freezing point than pure water, so an ammonia-rich ocean could remain liquid in places far colder than Earth. Envision a twilight planet where the sun never climbs high, casting a weak illumination over a sea tinted faintly green or yellow by dissolved ammonia. The air might carry the sharp scent of ammonia to any creature that could smell it, and crystalline water ice might float on an ammonia water sea like strange pale bergs. Under the surface, the chemistry is exotic. Ammonia carries hydrogen and allows unusual biochemical reactions. So if life arose here, it might use ammonia as our life uses water. The idea of ammonia-based life has long been speculated. On such a world, it could be real, with life forms swimming in what we would deem a caustic brew. But to them, it is as natural as an earthly ocean. To such creatures, ammonia serves as the lifeblood of their world. These strange seas under alien skies would challenge our notions of what an ocean can be. Instead of the deep blue of Earth's seas, a hydrocarbon ocean might appear nearly black or a murky brown from above, its surface slick like oil. An ammonia ocean might gleam pale yellow-green under an alien sun. The skies would also differ. A methane sea world could have hazy orange skies full of smog, as Titan does, while an ammonia ocean world might have a thin, cold atmosphere with wisps of white cloud. On some worlds, such exotic oceans might lie beneath thick hydrogen atmospheres, never seeing direct starlight, but glowing under perpetual cloud. On other worlds, a break in the clouds at dusk might let alien stars wink on the surface of a methane lake, much like stars reflecting off a still pond on Earth. This gentle glimmer reminds us of a simple truth. Even the strangest seas share a connection with the same cosmos. For all their differences, those alien oceans still reflect starlight, as our own oceans do. Could life exist in these alien liquids? Scientists don't rule it out. Any liquid medium, given the right chemistry, could potentially harbour life. It might not operate at the same speed or use the same biochemistry we know. Methane-based life on Titan, for example, would be very cold and slow, with metabolism trudging along at a molasses pace. But it could still evolve, grow, and reproduce in its own time frame. Perhaps there are creatures out there that swim in methane the way fish swim in water, their bodies using liquid methane in their cells instead of water. Or organisms that drift in ammonia seas, with antifreeze-like adaptations to keep their biochemistry fluid. If life can adapt to use these solvents, It broadens the definition of a living world considerably. It reminds us that what we consider water, a life-giving liquid, might have analogues in environments utterly unlike our own. As we search the galaxy, we keep an open mind for these exotic ocean worlds. We might detect the chemical signatures of ammonia or hydrocarbons in an exoplanet's atmosphere, telling us that something unusual is happening below. If we ever find a planet with a dense methane atmosphere in the habitable zone of a faint star, we will wonder, does it have seas of methane akin to a global Titan? Or imagine a super-Earth far from its star, but kept warm by internal heat, with a surface ocean of ammonia and water beneath a thick, insulating sky, a true icy haven for strange life. These ideas were once purely the realm of science fiction, but Titan's discovery changed that, showing that nature can indeed set the table for such alien oceans. Strange seas challenge us to expand our concept of habitability. They underline that the ingredients for oceans can combine in creative ways. An ocean doesn't have to be water to sculpt a landscape or nurture chemistry. To an intrepid explorer, a voyage on a hydrocarbon sea or an ammonia ocean would be an adventure into almost unimaginable conditions. One might row a boat through liquid methane under a dim orange sky, or navigate ice floes on an ammonia sea beneath shimmering auroras. Yet, in those experiences, however alien, there would be a thread of familiarity. Waves are still waves, flowing liquid still reflects light, and the desire to explore would be as strong as ever. The existence of such seas beyond Earth would be a testament to nature's boundless creativity. It's a reminder that for every way life has thrived on our planet, there may be countless other ways it could thrive on worlds strikingly different, where seas roll on beneath truly alien suns. For explorers and dreamers alike, such possibilities inspire us to imagine worlds beyond our own.